tab? Yeah. Oh, okay. So hopefully everyone could hear what I said up to this point kind of okay at least. Okay, so we have add 2, we have anchor. Add 2, we're saying the output is exactly 2 more than the input. Anchor, we're saying the output is greater than the input. This is not going to work for our verifier because we have what's known as a modular verifier, which means we're verifying the functions modularly. And the verifier is only looking at the specifications of functions that are called. It's not looking at the definitions. So what that means is here, when we're trying to verify add 2, we don't actually see this whole picture. We see this part of the picture. We see that anchor's output is greater than its input. We don't know anything else about it. So it could be that anchor adds 1,000,000. That satisfies the specification of anchor, violates the specification of add 2. Right? So that's kind of the potential problem you can run into with modular verifiers. You can have specifications that all look correct and then in fact are all correct, but then you can't verify them and it can be tricky to figure out why. In some earlier work before this paper, also with Ranjit and Ruzicka and also Anton Su and Maxwell Bland, we came up with this scheme to try to help people diagnose these errors that you get from a modular verifier. And the idea was these error messages you get from the verifier are kind of hard to understand, so let's give counter examples instead. Ideally, we give what's called a concrete counterexample, which is an actual input and output that violates the specification, right? If your specification is actually wrong, that's possible to do. In a case like with add to an anchor, the specification is not actually wrong, right? It's just not being proven. And so we came up with this notion we call an abstract counterexample to illustrate this kind of mistake. So to kind of show what an abstract counterexample is by example, here's an abstract counterexample for this add 2 case. It says that add 2 of 0 is equal to 3, violating add 2 specification if anchor of 0 is equal to 2. So the keyword here is if, right? Anchor of 0 does not equal 2, but anchor of 0 equals 2 is consistent with the specification on anchor. Oops, sorry, I haven't updated specification there, but anchor 0 is equal to 2 is equal to the kind of specification of anchor where the output is greater than the input. And it violates the specification of add 2 if anchor of 0 equals 2. So the way to fix this is to make the specification on an anchor stronger to rule out this kind of bad possibility of input and output, which is done by saying that the output is exactly the input plus 1. Now this add to anchor case is kind of boring and simple and can be easily solved by inlining or something also, right? But I want to point out that this gets more complicated and more interesting with more complex functions, right? And you end up in cases where you need like inductive proofs that can't just be done by inlining. So here I have a function concat. Concat has a specification that says the size of the input is equal to the sum size of the output. That sum size function is basically taking a list of lists and summing up the sizes of all the lists contained in the lists. So concat is taking a bunch of lists and sticking them all together. It relies on this helper function app that also needs a specification for verification to succeed. And the specification I have here is insufficient, so we could get a abstract counterexample there as well. I'm going to gloss over the details of this for now. The details of this abstract counterexample are not that important. So that's kind of the previous work, finding these concrete and abstract counterexamples. What we then said is, well, we're getting these counterexamples, can show them to the user. Hopefully they're helpful to the user in debugging. But really, it would be nice if we could just automate the process of modular verification and automate finding these specifications. So the natural way to do this, if you have counterexamples, is throw this stuff into a counterexample guided inductive synthesis loop or a CGIS loop. So that's what we're doing now. So we now have the code and the specifications written by the user, which is what we're going to try to prove. And then guided by abstract counterexamples, we're going to try to synthesize new specifications to support those user-driven specifications. As we synthesize specifications, we might also find concrete counterexamples to the synthesized specifications. Those can be given to the synthesizer to help guide it. We might find concrete counterexamples to the user specification. If we find a concrete counterexample to the user specification, we just return that to the user because there's no kind of ground truth to say, is the bug in the user's program or is the bug in the user specification, right? That's something they have to kind of decide and fix. This is the concat app program from before, but without a specification on app at all. So I'm just going to kind of point out app is called in the last line of concat there, right? And basically what app is doing is it's appending two lists together. And if you try to verify this, you're going to get a verification error because we need to know something about what app does. And we can explain the verification error you get with an abstract counterexample. If appending two empty lists gives you a list with 0 in it, then concat of a list with two empty lists in it gives you a list with 0 in it, which violates the specification of concat. So now we know that whatever specification we have for app, it has to say that two empty lists does not yield a list with 0 in it. We can also actually just run app for real on two empty lists and say, well, an app takes two empty lists and gives you an empty list, so the specification has to satisfy that, right? And so now we have two goals for a synthesizer. The thing that's indicated by the abstract counterexample has to be false. The real evaluation has to be true. And so we can synthesize a specification. Maybe the size of app's output is always 0, right? That is false when your output is a list with 0 in it. It's true when your output is an empty list. Well, of course, it's not a correct specification for app, right? And so then we get a concrete counterexample to our synthesized specification. And so we add that as a new synthesis goal. We now know that a list with 0 in it and an empty list gives us a list with 0 in it. And so then we can say, well, maybe the size of the output is the size of the first input. And then, of course, this is not sufficient because you might have elements in the second input. And so we get another counterexample. And we keep on doing this until we have enough counterexamples to guide us to a correct specification for app, meaning a specification that both is true about app, correctly describes app, and is sufficient to verify the specification on concat. We can prove some theorems about this. Soundness is somewhat trivial looking at the algorithm because we're calling the verifier over. Oh, I should say, by the way, these are informally stated on the slide, and look at the paper for details. Soundness follows pretty easily from the algorithm if you assume soundness of the verifier. Because basically what we're doing is looking for a set of specifications that let the verifier successfully verify the code. We run the verifier. If it verifies the code, we finish. Otherwise, we continue in the loop, right? So soundness is pretty straightforward. We can also prove some completeness properties relative to the verifier's ability to reason. So really, what we can say, and we actually state a more general version of this in the paper, but if there exists an assignment of specifications drawn from this grammar that would let the verifier succeed in verifying the code, we will find that assignment of specifications. The version in the paper is actually more general than this. It describes requirements for a synthesizer for a particular language that would let you state something like this. We implemented it in particular for a synthesizer that synthesizes Lea specifications. I'm going to kind of gloss over the details of that a little bit for time, but the basic idea is we're taking these Leah specifications and we're using an SMT solver to synthesize definitions. And so we have a bunch of templates that look like this, basically big if-then else's, just select do you want an equality, or do you want a less than, or do you want a greater than. This doesn't get you conjunction or disjunction, but as the synthesizer runs and fails to find a specification, we create the possibility for conjunctions and disjunctions of these in our template. There's some kind of tricky corner cases where you can run into things like the set of specifications you have has made other specifications you need unrealizable, or there's like no specification that you can synthesize given these other specifications. And so that requires backtracking, which requires using things like unsat cores to figure out where problems are. So using an SMT solver here lets us do some of that. We experimented with using Saiga solvers and such, but it wasn't quite enough to like get us where we needed to be. Yeah. So there's much more details about how all this works in the paper, and how exactly this corresponds to refinement types and how we get refinement types into the synthesizer and vice versa. We evaluated this on a mixture of benchmarks from prior work on liquid Haskell, some benchmarks from our prior work on concrete and abstract counterexamples, and a couple other case studies that I'll talk about. Most of the time when we're successful is spent on symbolic execution. Interestingly, when we time out, a lot of the time is spent on synthesis. So synthesis is usually pretty fast, except when it's not, and then it really slows us down a lot. We have a couple kind of, so these are all pretty small benchmarks, all terminate in under a minute. We have a couple larger case studies in the paper. I'm going to highlight one of them, which is an implementation of k-means, which has this one k-means one function that has a specification on it, and involves 34 other functions that we have to synthesize specifications for, including merge cluster nearest and centroid called in this function are functions with quite tricky preconditions. And so what happens with this is kind of interesting is we spend about a fourth of the time just symbolically executing k-means one, trying to find concrete and abstract counterexamples to illustrate what's happening with these functions here. And then everything else happens pretty easily with the other 31 functions or whatever it is. There's quite a bit more in the paper. Like I mentioned, we have formal statements of and generalizations of the theorems. We have much more on the Leah synthesizer and how that works. We have a little bit about synthesizers for other types, such as sets. And we have a bunch more benchmarks, including comparisons to some other similar tools, and evaluations on data structures from Okasaki's functional programming textbook. Thanks. I'm happy to take your questions.
All right, so we'll take a few questions. And if you don't mind, speak into the mic and please introduce yourself.
Hi, I'm Ravi Mangal. In practice, you would expect users to review the synthesized specifications.
Sure. I mean, they can if they want. They are, I mean, the code is verified based on the specifications, right? So I guess it's a question of how much you trust your modular verifier also, right?
If there's a mistake in the code and I synthesize the specification and that allows me to prove the overall theorem, then something has gone wrong, right?
So, yeah, so assuming the modular verifier is correct, if we say here's a set of specifications, let its verification succeed, then whatever your specification is that you wrote down is correct about the function you wrote down, right? Of course, it's always possible your specification is a bit wrong or your code is a bit wrong. So you should, maybe still examine things a bit yourself. But there's no possibility of or at least there's no way I can think of for our synthesizer to trick the modular verifier into verifying something that isn't true. Again, assuming the modular verifier is correct, right?
Thank you.
Yeah.
Did you try to, sorry, this is Madhu from UIUC. Did you try to look at the related problem of just synthesizing the strongest post-condition for modules independent of the client in your language, in some logic that, restricted logic that you can handle?
We didn't look at that specifically. There is work on that topic. I think you've done some work on that topic, right? Yeah, I mean, I think that there's, for this setting in particular, there's potentially an advantage to just saying, here's a specification that's sufficient to, because like typically we have some property we care about, right? And there's an advantage to just being able to say, let's find a specification for merge cluster that works, even if it's not the strongest. Because, if you make merge clusters post-condition stronger, then everything downstream from merge cluster also maybe needs something that's stronger, right? So it just slows down the process. The other thing that could be a bit of an issue is we're finding both preconditions and postconditions. So here, actually, most of the time with centroid and nearest and merge cluster is spent finding preconditions based on the preconditions for k-means 1. So you can always make your preconditions stronger and your postconditions weaker, or vice versa, right? So yeah, so I mean, and there's cases where you can't just rely on having the strongest postcondition here. You also need some preconditions. So I think for modular verification, it's not quite the right approach, at least all the time.
Okay, sorry, let's try to keep on track. So please take your other questions to the speaker after the session. Okay, so hand off the mic.
Yeah, I would have forgotten.
Is that good?
That should be good.
Okay.
Yeah, put it in any pocket. Don't fiddle with it. You should be all set.
Okay.
All right. Our next speaker is Celeste Barnaby from UT Austin.
Okay. Hi everyone, I'm Celeste Barnaby and I'm going to be talking about our paper, Choose, Don't Label, Multiple Choice Query Synthesis for Program Disambiguation. So recent advances in program synthesis and large language models have made it increasingly easy to generate code from high-level intent. You can describe the program you want in natural language and an LLM can generate code matching that description. However, high-level specifications may be underspecified or open to interpretation, giving rise to multiple plausible solutions that are semantically distinct. To contend with this, you can try checking candidate programs against test cases or input-output examples, but there may still be multiple programs that match these examples but have differing behavior on other untested inputs. So to address this ambiguity, prior work has explored active learning strategies that identify the desired program from a hypothesis space of candidates by asking questions that clarify your intent. This process continues iteratively until there's no remaining ambiguity about your desired program. These approaches, however, predominantly rely on users to provide outputs for concrete inputs, which has two key limitations. First, manual input labeling can be cumbersome and error-prone in structure-rich domains, such as those involving tables or nested data structures. For instance, if you're trying to generate a table transformation program, an active learning system might ask you to perform your desired transformation on an example input table. This can be difficult and time-consuming, and if you make a mistake, the active learner might fail to return your desired program. Second, most existing active learning methods reason over a fixed data set of inputs and therefore only guarantee correctness on those inputs. For instance, suppose we want a program that deduplicates tables by user item pairs. Existing active learning systems may synthesize a program that behaves correctly on a fixed data set of tables, but is not semantically equivalent to the user's intended program. For instance, if all the observed tables happen to contain at most one item per user, like this one, then grouping by user produces the same output as grouping by user item. And as a result, the active learner may incorrectly return a program like this, which deduplicates only by user. If we later want to apply this program to a new table where a user purchases multiple different items, the program no longer matches the user's intent. So here, if the user purchased 2 unique items, we want an output table that didn't deduplicate anything, but the synthesized program incorrectly merges these purchases together. So to address these limitations, we propose a new active learning paradigm in which, instead of asking users to label concrete inputs, the system generates multiple choice questions about high-level program behavior. So here's an example of a multiple choice query that our approach may generate. This question describes a hypothetical input table and asks what the output table should look like. The user then simply selects the answer corresponding to the intended program behavior. So under the hood, a query corresponds to a logical formula that represents a precondition on the space of inputs, and each answer option represents a logical formula that represents a postcondition on the output of the program. So answering the multiple choice query reduces to selecting which of several horse-style specifications represents the user's intent. We can use an LLM to translate these formulas into natural language, and the queries are designed to balance simplicity, meaning that they're easy for a user to interpret and answer, and power, meaning that they prune large portions of the hypothesis space of programs. Because these queries don't rely on concrete inputs, they can reason about wider classes of behavior than existing active learning techniques. So this work has 3 key contributions. The first is a new active learning framework in which users answer multiple choice queries about high-level program behaviors rather than labeling concrete inputs. The second is an algorithm for generating multiple choice queries that balances informativeness and interpretability. And the third is an implementation of these ideas in an active learning tool called Socrates and an evaluation over 4 synthesis domains. In the next part of the talk, I'll discuss the main components of our query synthesis algorithm. So first, let's formally define a query. In our framework, a query consists of a scenario phi and a set of k answers psi. Intuitively, the scenario describes a precondition on the input, while each answer corresponds to a different postcondition on the program behavior under that input scenario. Further, we require queries to satisfy 2 properties with respect to a hypothesis space of candidate programs. The first is mutual exclusion, meaning that each program satisfies at most 1 answer choice. And the second is coverage, meaning that every program in the hypothesis space must satisfy at least 1 answer choice. These 2 properties ensure that as long as the user's desired program is in the hypothesis space, there's always 1 correct answer present among the options shown to the user. So at a high level, the query selection problem is to find a query queue that balances 2 goals. The first is maximizing disambiguation power, meaning that each possible answer should eliminate a large portion of the hypothesis space. And the second is maximizing interpretability, meaning that the user can easily understand and answer the query. We can measure interpretability as the AST sizes of the logical formulas in the query. However, directly solving this problem is prohibitively difficult in practice for a couple of reasons. First, the space of possible queries is too large for exhaustive search to be feasible. And second, optimizing interpretability at the level of the entire query makes it difficult to isolate and control the complexity of individual conditions. So to address these challenges, we use a decomposed formulation where we first select a scenario phi that captures semantically meaningful behavioral distinctions while remaining interpretable. And we then construct simple discriminative answers conditioned on that scenario phi. So first, let's look at how we do step 1. Here, our goal is to synthesize a scenario phi that is both informative and interpretable. To do this, we first generate distinguishing constraints for each pair of programs in the hypothesis space. Intuitively, each constraint describes when programs behave differently. A little more formally, given two programs P1 and P2, we want to find conditions alpha such that for any input satisfying alpha, P1 and P2 produce different outputs. We then solve an optimization problem to find a conjunction of constraints that distinguishes many programs simultaneously while penalizing more complex constraints. The resulting condition becomes the scenario of our multiple choice question. Let's walk through an example. So first, we want to generate distinguishing constraints for a single pair of programs. For example, consider these two programs that filter rows from a table. P1 keeps rows whose price is less than 5, while P2 keeps rows whose price is greater than 20. We'd like to find some simple conditions on the input table under which these two programs produce different outputs. We can think of this as an abduction problem where we want to find simple input conditions that explain why programs behave differently. In this example, we can obtain two such constraints. The first states that a row has price less than 5, and under this condition, P1 would keep the row while P2 would filter it. The second states that a row has price greater than 20. Here, P2 would keep this row while P1 would filter it. We repeat this process for each pair of programs in the hypothesis space. So here, let's suppose we have a hypothesis space of 3 programs, and we can generate these sets of distinguishing conditions for each pair of programs. To find a single constraint that distinguishes many pairs of programs, we solve an optimization problem that searches for a satisfiable conjunction of constraints covering as many pairs as possible while remaining syntactically simple. We show the full formulation of this optimization problem in the paper. Intuitively, it allows us to synthesize scenarios that are highly distinguishable while still being easy for users to understand. In this example, the optimization problem selects the 2 highlighted conditions. These conditions can both be satisfied simultaneously, and their conjunction distinguishes 2 of the 3 program pairs while remaining simple and easy to understand. The conjunction is then simplified to create this scenario of our multiple choice query. Now let's look at how we generate answer choices with respect to the scenario phi. So given a scenario phi, we want to generate answer choices that partition the remaining hypothesis space as evenly as possible. To do this, we first group programs according to their strongest postconditions under phi. Intuitively, programs that behave equivalently in this scenario are placed into the same cluster. However, there may still be many such clusters, so we merge them to produce a smaller number of clusters. And finally, for each merged cluster, we synthesize an answer choice psi that separates that cluster from the others. Intuitively, psi I is a postcondition on program outputs that holds for all behaviors represented by its merged cluster and rules out behaviors from every other cluster while remaining as simple as possible. We've implemented these algorithms in an active learning tool called Socrates. So in the next part of the talk, I'll discuss our evaluation of Socrates. We evaluated Socrates across 4 synthesis domains from prior work. The first is the table transformation domain that we've looked at throughout the talk. The second is a JSON transformation domain. In this setting, the goal is to transform JSON inputs into structured outputs through operations like field extraction and flattening. Our third domain is image editing, where each task specifies a high-level image edit, such as crop all people wearing backpacks. Unlike the 2 previous domains, these tasks are neurosymbolic and require synthesizing programs in a DSL that utilizes vision models for image classification and segmentation. In particular, programs in this DSL combine neural perception, like detecting people and backpacks, with symbolic spatial reasoning over the detected objects. Our fourth domain, image search, involves filtering a subset of images that have a certain property, for instance, images where a bride and groom are standing next to each other. This domain also synthesizes neurosymbolic programs. Importantly, Socrates reasons symbolically about these neural components, allowing us to synthesize correct programs without relying on the accuracy of the underlying neural networks. We compare Socrates against 3 state-of-the-art active learning techniques from prior work. Because no single baseline applies across all our domains, we consider 2 groups of baselines. First, for the symbolic domains, we compare against sample size and learn size. Sample size selects inputs that maximize worst-case pruning power, while learn size effectively optimizes expected pruning power. For the neurosymbolic domains, we compare against smart label, which is the only prior active learning approach that provides formal correctness guarantees in the presence of neural uncertainty. So in total, we evaluated 157 synthesis tasks. To generate an initial hypothesis space for each task, we first generated 2 input-output examples and synthesized programs consistent with those examples using a synthesis tool, such as an LLM-based agent. Importantly, we ensure that the hypothesis space always contains the ground truth program, along with many other semantically distinct programs. To compare against prior active learning approaches, we also require concrete input spaces for each task. For the image edit and image search domains, we used the same image datasets from prior work, and for the table and JSON domains, we generated synthetic input spaces by sampling inputs from each domain's grammar. So our first research question asks whether Socrates is more accurate than the active learning baselines. So we measured the percentage of benchmarks where the synthesized program is semantically equivalent to the ground truth program. And overall, Socrates solves all of the benchmarks across our domains, while the baselines fail on 14 to 37% of tasks. Our second research question asks whether Socrates' queries are more interpretable than those of the active learning baselines. We conducted a user study comparing our multiple choice queries against the input-output queries used by baselines. And in particular, we asked users to complete active learning tasks both by answering multiple choice questions with Socrates and by labeling inputs with one of the baseline tools. We measured both response time and answer accuracy across 4 domains. So overall, users answered the multiple choice queries substantially more accurately, achieving 89% accuracy compared to 64% for input-output queries. And additionally, across all domains, users answered multiple choice queries faster on average. Our third research question asks how Socrates' efficiency compares to that of the baselines. Here, this graph shows average total tool runtime in seconds. So overall, Socrates achieves runtime comparable to prior approaches. In the image domains, Socrates is actually faster than the baselines. To better understand the active learning cost, we also evaluate an instant LLM variant that omits the processing time required to translate logical formulas to natural language with an LLM. And here we see that the underlying symbolic reasoning of Socrates is quite efficient and that most of the runtime comes from this LLM processing time. So finally, we return to the motivation behind this work, allowing users to trust that the programs they synthesized actually match their intent. Our key idea is that users shouldn't have to manually label low-level examples in order to establish this trust. Instead, we can ask users high-level questions that are easy to interpret, easy to answer correctly, and better aligned with semantic program behavior. So in this paper, we've introduced a multiple-choice active learning framework for program disambiguation, developed algorithms for synthesizing queries, and implemented these ideas in our tool, Socrates. So thanks for listening, and I'll take questions now.
If I'm understanding the approach correctly, it hangs on the ability to generate the hypothesis space first, understand what's in the hypothesis space in order to come up with scenarios and discriminating one of the things that strikes me is that like it can be expensive to generate a large hypothesis space in order to do this, and it's also anything that's non-exhaustive, you then have to start making decisions about which things to include in the hypothesis space and which ones to not. And some parts of this feel a little circular, right? But also it seems tractable because a lot of engineers, I think, will do this in their head. They'll kind of like sketch out a program in their head when they get the requirements, and they might ask new questions. Like, how are you handling managing the size of the hypothesis space, and how are you maybe optimizing around not having to generate something that's completely exhaustive in order to do this?
Yeah, that's a good point. So a couple thoughts here. Yeah, so first of all, Socrates is agnostic to the type of synthesizer you use and basically treats it as a black box. So if you're using an LLM-based agent, I think that generating like a relatively small set of candidate programs actually isn't that expensive. But in some cases where it is, or where you're using, like, say, an enumerative-based synthesizer where it's more expensive, in our implementation, we, when generating queries, sample a subset of the hypothesis space and generate an optimal query with respect to that subset. So that allows us to still generate queries efficiently, even as the size of the hypothesis space scales.
Hi, I'm Avel from UIUC. I think this is very good work. My question is, since you're already using LLM agents, have you also considered creating queries and scenarios using them? Because I think contemporary coding agents already do that, and have you compared against them?
So you're suggesting instead of doing this like symbolic reasoning at all, we maybe just like give the candidate programs?
The questions or the scenarios may not have the properties that you described, but they still may be useful in guiding the search.
Yeah, I think an LLM probably could generate like discriminating scenarios from candidate programs. I think here we're really focusing on these guarantees of correctness and establishing like user trust that the program they receive is correct. I think future work could potentially like integrate like AI techniques more in the process of that, but that was our main focus here.
Thank you.
Hi, I'm Aditya from UW-Madison. So I have a question about the active learning paradigm that you're choosing, right? And it's a riff on some of the questions that have already been asked. So you're using active learning to cut down on the hypothesis space by having like the sense of contracts and your test cases in mind. Now, there's really also the element of most likely program and things like that that you can leverage if you're learning over lots of data. So have you considered that for the active learning model itself to be something where you ask like plain English, clarifying questions to the user, forget scenarios, forget all of that, right? I'm suggesting a completely different paper at this point, but seeing as you're advocating for this paradigm, I'm asking if it might be better to ask these questions that might tease out what the user is thinking about. The hypothesis space can be as large as they please, and you just find the most likely program that is consistent with the clues they've given you so far. There's no need to pin it down exactly, right?
Right, yeah, I think reasoning about like which programs are more likely is a really interesting problem, and I think that could also...
And you only clarify to that extent, right? There's no need to pin it down completely. You only ask clarifying questions so that you get the most likely program that the user is thinking about.
Right, yeah, I think that's an interesting line of future work and could... yeah, I think that's another instance where like we could have the AI agents like integrated more into the active learning system, and like that could potentially be more efficient, but again, it also risks like having that uncertainty. But yeah, I think that's a good idea.
Okay, let's take the rest of the questions offline. Speaker is Ray Don.
Hello everyone, I'm Ray from the University of Michigan, and today I will introduce our work, pre-synthesis. It's a program synthesis paper, and we're trying to explore a new dimension to scale up the program synthesis. This work is done at the University of Michigan with my collaborators Qingyue Wu, Danny Ding, who is at the UT Austin now, and Zheng Guo, Ruiji, and my advisor, Professor Xinyu Wang. So the question we'll ask here is, how do we better perform the synthesis? Previous works have pushed many fronts on this topic. So for example, they explore the different search algorithms, search space representations, pruning mechanisms, and ML AI-guided prioritizations. So all these are asked the same question, what to do during the synthesis? But we ask a different question here, when to perform the synthesis? So say you have a lot of resources, right, but you don't have it online after the synthesis task is given. If you have resources before the synthesis task is given, what you can do? So in this work, I will introduce an idea called scaling up by offline pre-computation. We name it pre-synthesis because it happens all before the task is given. So let me set up the problem first. In this work, we are considering a problem program by example. So it's a long-standing problem in this community, and it can be a foundation to many different applications. So basically, the user will give an I/O example, for example, 0001 to 0110. So this is a bit vector. And the user will provide you a DSL. For example, in this DSL, you can keep adding 1, adding 2, left shift 1, and left shift 2. And you feed this to the synthesizer. And the synthesizer will return you a program that satisfies the specifications. For example, in this case, X left shift 2 plus 2. So the synthesizer here, what it should essentially do is to search over a program space. As the program space could be large, this procedure could be slow. One way to speed up this is to use abstract semantics to prune, and it's also well studied in this community. So basically, you have examples here, and you have abstractions. For example, here, the abstraction could be the last bit. The last bit of every value could be 0 or 1. And the idea behind this is that it can divide the program space according to the program's abstract behavior into a finite set. So for example, X plus 2 and X shift 2, left shift 2 plus 1 all takes an input with last bit 1 and output with last bit 1. So now, say our output is not ending with 1. So we can prune away the space. The idea is that it can prune families of programs without enumerating them. And abstractions have different granularities, as you may know, and finer abstractions can prune more. I showed you how to use last 1 bit, but of course you can use more bits, for example, last 2 bits and last 3 bits. As you use finer-grained abstractions, you can divide the program space into more pieces, because now you can distinguish different program behaviors. And when you prune them, you can leave fewer programs, and the search space will be smaller. Well, everything is good here. But it comes with a cost. So as you use finer-grained abstraction, although you can prune more programs, modeling the space itself is very costly. And our idea, before our idea, okay, so the total synthesis time equals to the enumeration time of the search space and the time to prune the search space, right? So as you use finer-grained abstraction, the enumeration time will decrease because you are enumerating less programs now. But the cost to prune the search space increases. So if you add in these two together, you will find the total synthesis time will first decrease as you use abstraction finer-grained, and then increases. This is because eventually the pruning cost will outweigh the benefits of the pruning itself. Our goal in this work is very simple. We want to use finer-grained abstractions, but we don't want to pay the cost too much. To realize our goal, our key idea is pre-synthesis. So we divide the synthesis procedure into 2 parts, offline part and online part. We define the online part as you see the specifications, right? And offline is before you see the specifications. So in our framework, the I/O example will query something from the offline, And then the offline will return a prune set of programs. So that means something is pre-computed offline. What we pre-computed? First is we do the semantics modeling of the whole program space. It's like a database of programs and their behaviors. And also, we have a part called reachability oracle. So this is an index of this database, because querying the database is better to have an index to make it faster. And we call this pre-synthesis because we pre-compute it offline, which means that we can pre-compute this data structure without seeing any examples. Let me show you how we do this by some by some running examples. So to understand how our framework works, let me first introduce you what to do without the offline part. Right, so I'm using the same DSL here, the same example, and we're using the last 2 bits as an abstraction. If you visualize the search procedure, right, it can be visualized as building a graph. For example, the node here is the value, and each value is marked with a grammar symbol, so you know where it comes from. For example, the base case here is our input, last bit 0, 1, and 2 in the grammar. And the edge in the graph is DSL operators. It means that you apply the DSL operator to the input and left shift 2, and you will produce a value. Last bit 0, 0. And you can keep applying it, and you get new values. After you apply every operators and saturate, you will get this graph. So this graph basically contains all possible programs and values we can get from our input, last bit 0, 1. And the synthesis actually is a graph query problem. You see the input here, and you see the output here. What we want is the reachable part between these two input values and output values. It contains all the programs that satisfy the abstract specification. So take a step back. Everything is done online, all right? So this is what we built in step 1, but what's really useful is actually a tiny portion of it. So the question is that, can we get the useful part without building the representation during the synthesis? Because building the first graph, is very costly. I'm only showing the 2 bits here, but what if you use finer grained abstractions, right? If you use like 3 bits, 4 bits, it can only be larger. Let me show you our first component, semantics modeling. It's a database of programs and their behaviors. So the idea is to pre-compute the graph I showed in the previous slides. There are some challenges, of course. For example, you don't know any input-output examples, what you can build for, right? Our idea is that we build for all possible inputs, so that whatever your online task is, I can always get something from our offline built structure. And of course, all possible inputs are infinite, right? So our idea is to use abstractions to reduce the infinitely set of values to finite set of abstractions. So our idea here is that we pre-compute the search space for all possible inputs using abstractions. I'll show you how we do this. So this is the DSL I used before and the abstraction I used before. So the base case, of course, is that you construct the nodes for all possible abstract inputs and also some values from the grammar. And you can follow the procedure I described before. So you grow this graph by applying DSL operators. And you can keep doing this until saturation. I'm only restricting the depth to up to 3 because I want to make things finite and bounded. And then when you see the I/O examples, you know what to do, right? It's actually, you can abstract the input and output to its abstractions values. And then the search procedure is actually a graph reachability problem. You start with the input and get all the forward reachable parts from our inputs. And you get all the backward reachable parts from our output. So you intersect these 2 portions, and you get the desired useful part as I showed before. So extracting solutions here is actually a bidirectional reachability problem. Yeah, so this is the input, this is the output. So you're basically querying this graph. what I showed you is how we build the offline thing, right? But if you do it naively, you do the naive graph querying, it will still be very slow because you still need to touch most part of the graph. So our second idea is to build a reachability oracle. It's like an index of the database to speed up the searching. So what it do is exactly to answer the query I showed before. So you give an input and output, and it will return a part that is useful. In our experiment, we encounter offline graph with about 500,000 nodes and 500 million of edges. And the reachability oracle is designed to answer bidirectional reachability queries efficiently. And I'll skip the technical details now, and please refer to our paper if you're interested. So since we moved the heavy computation to offline, and online is just a simple graph querying problem, we can use finer grained abstraction, but without paying too much cost. And our goal is achieved. So let's talk about the evaluation. We implement our tool called Foresighter because it has the foresight of the search space as you build it offline. There are some key questions that you may concern. First is, how does Foresighter compare with baselines for different application domains? And the second question is, can Foresighter solve faster with finer grained abstractions? We evaluate our tool on 3 different application domains: string transformation, matrix manipulation, and SQL query generation. Our tool can outperform existing tool on all 3 domains and is generalizable to more domains. I'll emphasize on the SQL query generation domain because it's the hardest and it has more than 3,000 benchmarks from previous papers. So this is the figure where it shows how many benchmarks can be solved within a given timeout. So Foresighter, the top curve, outperforms all existing tools. And the second question is, can Foresighter actually solve faster with finer grained abstractions? Because previously the figures I showed is conceptual. So what about the real data? So this is a graph that shows how the normalized solving time changes with different abstraction granularities. So for the abstraction granularities, the leftmost is the coarse-grained one, and the rightmost is finer-grained one. And if you see the red triangle line, this is build everything online, right? The curve is like a U shape, I said, demonstrated before. So as the abstraction granularity becomes more finer grained, it will first decrease, but eventually increase dramatically. That's because the pruning cost eventually dominates the time. And for Foresighter, we can continue to decrease the total solving time as we use more finer grained abstraction. So our goal is achieved. And using Foresighter, you can use finer grained abstraction online, but without paying the cost. So in conclusion, we introduced this offline and online paradigm, and our implementation is evaluated to be reusable and available online. And we welcome you to check out our paper and implementation. And thank you. I'm ready to take questions.
I'm Sishan from UIUC. Assume that you have to do pre-computation for different domains, right?
Yes, so if you are given DSL and abstractions, I will need to pre-compute the graph for different domains, yes.
I'm just wondering how costly that is.
Oh, how costly. So I do have some numbers. So for example, in our SQL generation domain, that's the largest problem we consider, right? So we take about 7 hours to build our offline graph, and we take about 5 hours for the index. And the final product of the offline graph is about 51 gigabytes. Yeah. But you may wonder, we spend a lot of resources here. Is that a problem, right? So our use case, imagine, is that we have some service provider and we have some clients. And the synthesizer is acting like a service. So basically, when you provide a synthesis service, you can pre-compute using a lot of resources. And when the client have their problem, they can just send the task here and it will return the solution. So we don't really require a lot of resources from the client side. Yeah.
Yeah, I really like this work. So one question I have is, like, the program space is exponential as like you get more as the size of the program gets larger. So
Yeah.
I wonder if I've considered if we can build a database incrementally as we get more queries. So initially, maybe we have a small database, but like then over time, we can specialize the database to the workload we have. Have you thought about this?
Yeah, incrementally build this search space is, of course, a way to extend this. So in this work, I'm assuming that the DSL is given is fixed and the abstraction is fixed. But you can use more fine-grained abstractions or tune your search space based on your need. I think that's a future direction, very interesting, but we haven't considered in this work. Yeah.
I have a question. So I like to build, sometimes I build super optimizers.
Yeah.
And so, you know, we run into exactly the problems you're talking about.
Yeah.
So can I use it?
Well, I think the key problem is that you have to define abstractions for your super optimization problem, right? So for example, here, the SQL one, we have some abstractions like the size of the table, the type of the table, but what's the abstraction in super optimization? That's a problem, right? That's orthogonal to this work. But if you have a good abstraction, you can build upon our work.
Well,
Yeah.
maybe we should talk.
Yeah, sure, thank you.
Yeah, I have a question. What if, for example, in your DSL, you allow some expressions that can build from other expressions? For example, if statement, so basically condition can be nested from other statement also like this. So, and this recursion can be basically infinite if you want to like brute force it for search. So is approach going to be applicable for programs like this, for DSLs like this?
Yeah, so currently what I'm showing here is that we have a bounded DSL, right? So you bound the maximum size of the DSL, for example, the depth of the DSL. And I think your question is that what if you have, for example, recursion, something like that, right? Well, in our work, I think our representation, the graph, is better to be applied to this kind of without loop, without recursion. And if you want to support like more fancy, for example, loop and recursion, you may need to consider another representation. I think it's an excited future work, but we currently do not have a good way to handle the like recursions. Yeah.
So the paper, the project uses a program by example as a means to like verify like correctness of the like synthesized program that the pre-synthesis process goes through. Is this approach also compatible with using formal logic-based requirements statements instead of just like individual like input-output examples? And if so, like what would be required or what would be necessary of the like acceptance predicates and abstractions in order for the whole modeling process to remain like sound and complete when like deducing down to
what kind of a domain you're trying to consider? So for example, what's the specification you're trying to consider?
Just something that represents entire like sets of input-output examples by a certain pattern rather than just individual examples.
Yeah, I think we are not restricted to like concrete examples. Anything that you can abstract behaviors to a finite set, we can, and if you can write the abstract transformer, which stick to the abstract semantics, I think you can use our tool. Because all we need is abstraction and the abstract transformer, you know.
Okay.
Yeah, and the mapping between the abstract value and the concrete value, or the specification. Yeah, we can talk offline.
Okay.
Yeah.
Okay, let's thank our speaker again.
Just want to make sure we have an extended display as opposed to a... Oh, wow. That is very grainy.
Try again. Just plug it back in.
Turn off what? I think it's good. I think so. We'll see. Yep. Yeah, am I audible on the? Okay, great.
Okay, our next speaker will be Abhishek Upar.
Shouldn't touch the wires. Okay, let's do this. Hi everyone, I'm Aditya, and today I'll be talking to you about our work in exploring a new style, perhaps a new paradigm of for providing guarantees for software. This is joint work with folks at the Indian Institute of Science, Bangalore, the University of Illinois Urbana-Champaign, and I'm at the University of Wisconsin-Madison. I want to start by getting us all to think about what the state of automated verification is today. And if you think about it in the landscape of specification complexity and code size or code complexity, we really have an either-or kind of situation, right? So you can have your favorite separation logic, recursion, quantifiers, what have you, and then if you want automated verification, you really can only do smaller programs. Or you can have something like lightweight types, and then you can really scale guarantees to large code. But when you have both complex specifications and large code, there isn't really like a systematic study or a science behind how to kind of approach this problem. And in our paper, we focus on a particular use case where you have a smaller client that uses a larger library. Now, this is actually fairly typical for a large class of programmers because, a lot of programmers, they don't really write libraries on a daily basis. What they do instead is they write smaller programs for their particular applications, and they just use convenient abstractions that are established and available elsewhere for, managing a queue or, calling things over a network and so on. And so this is the problem that we look at in this paper, and we want to think about how do you establish guarantees for this kind of software. So, in a nutshell, this is the one-liner of the entire work. Our argument is that you verify the client and you test the library. Let me say that one more time. You verify the client, but you test the library. Let's actually look a little bit into what this means. In classical verification, when you have this like client calling a library kind of setup, what happens is that you have to come up with contracts at the interface for the library methods such that on the one side, you verify the client assuming the contracts for the library that you came up with. And on the other hand, you also have to show that your library methods do indeed satisfy these contracts. What we're recommending is that you just drop the latter condition and you test the contracts instead, right? Let's, you might be asking, why is this a reasonable thing to do, right? Like, what am I talking about in terms of verification? And to do that, let's zoom out a little bit and think about what we mean by guarantees for software, right? So you're really thinking about the situation where you're writing a smaller program and you want to avoid bad code, right? You want to avoid, doing something stupid in your code. But if you're writing a smaller client that's calling the standard Java container for queues, it is very likely that you're not going to have these bad behaviors inside the library. What's more likely is that you're going to have these bad behaviors inside either your own code or in the way that you're calling the library, right? So if you think of this as the kind of threat model or the kind of bad code practice that you want to avoid, what then falls out is that maybe it's reasonable to make sure that you verify whatever you're writing, the suspicious part, very, very well, modulo a high confidence abstraction of something that is more well established. And so that is, in a nutshell, the essence of the paradigm, right? So I want to formally define what this is. We call it the VMTLC problem, the verification modulo tested library contracts. Given a client with some specifications, which calls a library, you synthesize contracts for the library's methods such that A, you verify the client assuming these contracts, and B, a test generator given a bounded resource budget does not find any input that violates these contracts for the methods. Now, mind you, we are in the setting of completely automated verification. So when I say you have to verify the client, if the client has loops or anything else, you have to come up with loop invariants or any other annotations that are required. So that is the problem.
Okay, let's just look at an example to shore up our intuition, right? So here is an example of a client that uses a set library. In this work, we operate in the setting of object-oriented programming. So we have encapsulation, so you don't get to peek inside the implementation of the set. What you're given instead is a set of observer methods. This is a fairly standard thing to do in object-oriented verification. Observer methods are like mathematical functions, essentially. They're side effect-free code that give you a view or a measurement of an object at a particular point. And so for a set, you can have observer methods like, is the set empty? What is the size of the set? And what is the minimum element in the set? Right? So these are some observer methods that you can have. Now I also have a client for you. This is a simple one for the purposes of this presentation. It has 2 loops. In the first loop, it just adds a bunch of non-negative integers. In the second loop, it drains the entire set and adds them all to an accumulator called sum. And what you have to prove is that the sum is non-negative, which of course it is. So given the VMTLC problem we've just looked at, I want to come up with contracts for the methods that the client uses, namely insert, remove, and empty, such that, as well as loop invariants for the client for the 2 loops, such that I can verify the client, and then separately, I can also test the contracts that I came up with for these methods and make sure that I can't find any input that violates these things. In this work, we encode verification conditions as constrained horn clauses. If you are not familiar with CSCs, ignore this slide. For the people who are aware, we encode them as CHCs. And so basically, you have unknown predicates corresponding to the 2 invariants, as well as the contracts that you want to come up with, and the verification conditions say exactly what you want, right? The beginning to the loop invariant, and all that stuff. Okay. So here are some contracts that you can come up with. So for insert, you can have a contract like if you either have an empty set or you have a set whose minimum was already non-negative, and you added another element that was non-negative, then you get another set whose minimum continues to be non-negative. And you can do similarly for remove, right? If you have a set whose minimum is already non-negative, anything you pull out of it is also non-negative, and then you have a set that continues to be minimum non-negative. Okay, and the loop invariants say exactly what you think they say. The first loop that adds the elements into the set says either had an empty set, which is the beginning, or I have a set with a non-empty minimum, with a non-negative minimum. And the second loop says either I have a set with a non-negative minimum, or at the end the set will be empty. And crucially, these invariants are maintained by the fact that the contract for insert and remove promise you that after you insert or remove, you continue to get sets with non-negative minimum. And using that, you can prove that the accumulator remains non-negative at the end. Good. Now, this is standard verification. We are familiar with this. But then you also want to make sure to have a test generator throw a bunch of well-behaved, well-formed inputs at these contracts and make sure that you can't find any behaviors of insert, remove, or empty that violate the contracts that you've come up with. So in contrast, if you had come up with something like, you know what, insert is going to be such that anything I insert, I'm going to get a set whose minimum is non-negative. The test generator, it'll clearly help you prove your client correct, but a test generator can easily say, you take the empty set, you insert like -5, and then clearly your contract is not true. So that's how that works. Okay, so we've gone through this exercise of verify the client, test the library. Now that's the first contribution of our work. Before I talk about the second contribution, I want to take a moment to reflect on what the real problem we're solving is, right? Once you think about this kind of hybrid guarantee that's not really testing, that's not really verification, it's kind of somewhere in the middle, and then you think about what you're really wanting the guarantees for. You want guarantees for the client program that you're verifying, right? We've established this at the beginning numerous times. So if what you want to do is prove your client correct, then the abstraction that you need for your library really only needs to be the abstraction that you need for your client, right? You only need a view of the library insofar as it is useful to prove your client correct. Now, what this opens you up is this idea of a contextual contract, right? So you have modular contracts, which we're all familiar with, and I presented to you. These are contracts for library methods that are universal. They hold for all possible inputs. In another sense, they basically are true for any client that might use the library methods. On the other hand, you can have contextual contracts, which you have one contract per call site. So if my client had 2 calls for insert, I'll have 2 contracts, 1 at each call site, such that these contracts are valid at that particular point in the program. And what this amounts to is really you're saying that they're valid under an implicit precondition. And what is the implicit precondition? You just collect all the reachable states that get to that point of the program and say, under that precondition, this contract is valid. That's what a contextual contract is. Now, why are these useful? Well, because they can actually give you a lot of leverage and can be much simpler than modular contracts at times if you want to establish guarantees about your software. So here's the example again. This time, I'm not going to give you the observer function min. And this is a problem because I liberally used min in my example earlier. I told you things like if you had a set with a non-negative minimum and you did something, it'll continue to, like you can't do any of that right now. And first of all, you have encapsulation. So you cannot break encapsulation, look into the set and go, you know what, I'll just write a minimum function. Like that's not happening. Secondly, even if you somehow manage to do that, you probably have, let's say, it's implemented as a list, and then you have to write a recursive function to compute the minimum, and then your verification goes for a toss. It just becomes much harder. So modular contracts, you're going to have to do a little bit of gymnastics, and then maybe it might or might not work. In contrast, look how absurdly simple a contextual contract is. You just say, let's say for remove, no matter what element I pull out, it's going to be non-negative. And why is this okay? Because under the implicit precondition at that call site, it is in fact true that no matter what element you pull out of the set, it's going to be non-negative. I really only added non-negative elements to the set, so of course it's going to be true. So contextual contracts in general can be simpler and easier to come up with. And they still help you construct a kind of this hybrid guarantee about your client code. The third contribution of our work is to come up with a solver, a pipeline for establishing these VMTLC style guarantees. And this solver interacts, has an interaction between a generalizing CHC solver, I'll tell you what that means in a second, and a test generator. The CHC solver is given the verification conditions for your client, and the test generator is given the code for your library methods. What happens is that the solver tries to come up simultaneously with loop invariants and contracts for your library methods. Once it does that, it sends the contracts over to the test generator. The test generator then looks at the contracts. If it's happy with them, yay, you're golden. If it's not happy with them, it'll come back to the solver and say, no, these contracts are not right. Here's an example. And the solver takes those failing examples into account and tries to come up with another set of appropriate loop invariants and contracts that can still verify the client. And this loop keeps happening until both entities are satisfied. Now, one of the key things that we realized while doing this work is that you really need a generalizing solver and not just some CHC solver. And why is this? It's because if you encode the problem at hand as a CHC along with all these like extra things saying, oh, all these buggy things that I've found for buggy instances I found for previously proposed contracts should be avoided, a generic CHC solver can just keep narrowly avoiding this and keep giving you like contracts that are still slightly wrong. Whereas you really need a solver that looks at all these failing examples that you give it and say, you know what, all these are symptoms of something else that has to be satisfied, namely the test generator, which is like hanging out in the back and it has some hidden expectation, and tries to come up with a general contract that will satisfy both requirements. And I'll show you some experiments where we tried like a regular CHC solver. In our work, we implement a generalizing CHC solver using the combination of an ICE learner. This is a learner established in prior work. I'm not going to go into it during this talk, as well as a regular constraint solver. And what ends up happening is this like very nice inner learning loop that happens inside this outer learning loop that between the solver and the test generator itself. There are more details in the paper. I would really encourage you to look at it. Okay, with that, I really want to move on to talking about the results of the paper. I'm going to flash some numbers and talk about what our evaluation revealed to us. We implement 3 learners for our ICE learning for the contract and loop invariant synthesis. We used Horn ICE, which is an ICE learner from prior work. It synthesizes decision trees. We also just threw an LLM at the problem, because, well, of course. And then we also constructed a hybrid solver that comes up with flexible, can flexibly come up with atomic predicates, which are then fed to the decision tree learner. And so these are the things that we came up with. Crucially, even though we use an LLM, mind you, all the contracts are vetted, like doubly vetted, on the one side by testing, on the other side by verification. So you really cannot get away with proposing unsound things. We implement these in a tool called Dualis, and we evaluate Dualis on a suite of benchmarks drawn from real-world libraries and competition problems. Crucially, we wanted to make sure that our problems are beyond the state of the art, so we threw all of these problems at Seahorn, which, as far as I know, is one of the state-of-the-art tools for completely automated verification. And Seahorn could only solve 7 out of the 43 problems in our suite. And more importantly, it was bad even when we gave it the library contracts. Right? And this really shows that the size of the problems and the complexity of specifications really do lie beyond the state of the art. And we have libraries that are like up to 3,000 lines of code. here are some evaluation results. It should be surprising to absolutely nobody that LLMs are doing very well, but I would encourage all of you to take it with a pinch of salt, because I think there's a lot of headroom for the hybrid solver to do better. We're looking into doing a larger study, and I think some of these results might change. What I do want you to pay attention to is the fact that when you ask for guarantees to be established using contextual contracts rather than modular contracts, you get better numbers, right? Because contextual contracts, as we discussed in the example, can be simpler and easier to synthesize in many situations. And the experiments reflect that. Okay, so the second I said testing, I know like 90% of you have been waiting to ask, are the contracts valid? Don't worry. You are my people, I've got you. We did absolutely do this study. We looked at all the synthesized contracts, both modular and contextual, for all of the benchmarks in our suite, and all of them were correct. We believe we did a mix of manual and automatic vetting, and with high confidence, we believe that all of these contracts are indeed correct. Now, we also did this experiment on an adversarial suite where we constructed programs where we artificially injected bugs that are hard to find for a test generator. By that I mean like we injected these very long paths that are rare, and it might be hard to get to these points. We injected such bugs. And even in that suite, for about 30 programs, when we asked our solver to come up with modular contracts, it said, no, I cannot come up with any, which is good. They're wrong. You should not be able to come up with contracts. And this speaks to a subtlety that, in the work, which is that it's actually pretty hard to come up with a generalizing hypothesis that somehow satisfies a test generator, helps you prove the client, and is somehow still wrong, right? And I think there's something in there that is worth exploring further. Now, of course, this was not true for contextual contracts. And for our 30 programs, there are about 11 programs where the solver came back and said, hey, I found a contextual contract, and it should not have been able to. We also looked at just using a plain CHC solver. I think we used CVC5 instead of a generalizing CHC solver, and it performed pretty badly. So it really looks like this idea of generalizing from the failures and having it be incorporated into the contract and loop invariant synthesis is essential. Okay, with that, I'm done. So my takeaway, this is the mantra, right? Verify the client, test the library. That's what we're advocating for. And in doing so, we've, I hope I've presented to you the possibility of a new point in the design space for establishing guarantees for software, this paradigm of VMTLC, verification modulo tested library contracts. I've also introduced to you the idea of contextual contracts that can be stated in the client's calling context, which may be simpler to state and synthesize, as well as a counterexample guided learning framework that combines a test generator and a generalizing solver to to establish VMTLC style guarantees. Thank you. Oh God.
Hi, Michael Emmy from Amazon Web Services. Really
Yeah.
interesting talk. I'm just wondering what you think about the potential risk of contextual contracts relying on implementation details that are not like totally stable and are kind of not the encapsulated object, but kind of maybe like a hash set would satisfy this, but a linked hash set wouldn't.
I see. Okay, let me try and repeat your question to understand. What do I think about the possibility that contextual contracts might end up relying on implementation details as opposed to the interface itself, where you have like one kind of hash set versus another kind of hash set? Is that the question? So, I don't quite see why that would be. Like, do you have some intuition for why you think that might be the case? I don't see that as being a risk, right? I mean, in contrast to modular contracts, somehow you seem to be contrasting with modular versus contextual, and
yeah,
I don't see
for
why.
instance, you have a set interface in the current implementation that you're using is like a tree set which returns first like the minimum element or whatever it is, and then later someone wants to change that to a hash set or some other kind of then you would really be relying on the underlying sortedness of that data structure that's not part of the set interface.
Right, but this is also true for modular contracts, right? In the sense that what if you observe behaviors and your vocabulary allows you to express something that is very specific to the implementation? Is that right?
Yeah, but the modular set contract wouldn't, appeal to a specific order there in that case.
Right. Yeah, it's an interesting question. I think maybe it's worth talking more offline, because I think there is some, okay. So first of all, there is an element of generalization involved, and clearly modular contracts generalize more, which is why you would avoid things like these implementation details. One of the things that is the hidden element that I have not spoken about at all in this talk is the vocabulary, right? So if you have a good set of observer methods, I would suspect that it might be possible to avoid over-relying on implementation details. Now, there is other work that we've cited enormously in the paper that tries to synthesize like very strong contracts and things like that. So you might want to consider synthesizing even contextually a stronger contract, and maybe that'll avoid the kind of problem that you're talking about. So I think of this as a generalization issue, the way, does that make sense? And I'm happy to talk more offline.
Miriam Kim at UCLA. I have a question about test generator part.
Yep.
Like, so it seems like you are checking contract like by testing the libraries, but you know AFL++ is not a property-based testing; it's just a fuzzer. So I'm kind of curious about how you actually test the contract. You know, because AFL will require like driver generation or fuzzing entry point, right? And the second question related to that is that for like contract that involves like stateful effect, how do you model the driver generation?
Okay, I understood your first question, so I will answer that, and then we will get to question number 2. The first question you're asking is, what is the entry point for the tester, and how do you construct the test harness, right? So the test harness is, roughly speaking, you just construct a bunch of well-formed objects, a random set, and you test with those set of randomly selected well-formed objects. In an earlier version of the tool, we used PECs, but for numerous reasons, we moved away from it. So there's no fundamental reason you can't use a property-specific test generator. In fact, in my opinion, it's better to use something that's property-specific because we're trying to look for contracts that prove a specific client, right? So, and for contextual contracts, you construct well-formed objects and all that, but you make sure that the entry point is only through the client. Right, so you construct well-formed objects not for the library methods, but for the client, and then you then like take the reachable path, and those are the inputs that you take. So I didn't quite understand question number 2.
Question is related because basically it's also about like constructing the program state where the client library could be invoked, right? So I think you mentioned that you're doing it through the client like program invocation, but we could talk offline.
Yeah. You just have to figure out what the randomly constructing well-formed objects is fine, right? That's obvious. And you then have to figure out what the entry point is. For modular contracts, the entry point is the library method itself, which is just tested in isolation. There's no context to the client. For the contextual contracts, you reach them through the client. So you write a test harness that is specifically constructs calling the client first, and then via that you go to the particular libraries. And yes, for what it's worth, I do think we should be using property-specific, property-driven test generators.
Okay, I'd like to keep us on track so you all can get to lunch on time, so let's move on to our last talk.
Yep, thank you.
Thank you.
Thank you.
No, a little lower is fine. Yeah, that's good, that's perfect. Put that in your pocket.
Okay. Thank you.
Okay, our next speaker will be Dongjae Lee.
Hello, I'm Dongjae Lee. Today, I will talk about expector extracting format specification from natural language intent. Spec-driven development is emerging now thanks to the AI. If we directly ask AI to implement code, then code quality becomes really poor and it is hard to control the model. So instead, in the spec-driven development, we write the specification first and then move on to the implementation. Then code quality improves, and it is easy to control the model by modifying the specification. To enjoy this advantage, many of AI coding tools support spec-driven development workflow. Kiro and SpecKit officially support spec-driven development. Codex, Cloud Code are supporting plan mode, which is very close to spec-driven development workflow. The core assumption of spec-driven development is implementation is satisfying specification. But the problem is specification is written in natural language, not a formal language. So the only way to check it is manual inspection or simply asking an LLM again and again. So people are starting to introduce formal verification. If we use formal verification, AI implement code and proof as well. Then proof checkers check the correctness of the proof. But another problem comes along. Writing formal specification is much challenging than writing natural language specification. So expect to address exactly this problem, and we convert by converting natural language intent into the formal specification. I will explain how expect works by using this coding test-like problem. Here's the problem description in natural language. First, a field is n by m grid consisting of words and empty cells, like this. If you place a bomb at x, y, all words in row x and column y are removed, like this. So the goal of the program is determine whether it is possible to remove all words with a single bomb, and if so, return the value of x and y. In this case, it is possible when bomb is placed at x2 and y5. Most of the existing methods generating formal specification from natural language intent are monolithic. It means they generate formal specification with single interaction with language model. This is the example from our baseline. Because they use monolithic method, high cognitive burden imposed on large language model, and it leads to wrong condition and duplicate codes, unnecessary loop. One of the solutions to address this problem is just extract single constraint from the natural language intent. But naturally, it leads to oversimplified condition, so we cannot detect bugs in the implementation by using this specification. In contrast, expect to generate correct and modular specification compared to the baseline. The main function of the specification is correspond to the main goal of the program, and can be mapped to the third statement of the natural language intent. And valid pose, which checks the given coordinate is in the field, can be mapped to the left side of the first statement. And wipes all, which represents the effect of the bomb, can be mapped to the second statement of the natural language intent. And lastly, is wall, which checks whether given coordinate is wall or not, can be mapped to the right side of the first statement. As you can see here, expect to generate specification is not only correct, but also easy to map to the natural language intent because it is modular. So expect to generate more correct specification, and most 2.8 times more correct specification compared to the baseline. And it generates easy to understand specification compared to the baseline. Here's the overview. First of all, users provide their intent in natural language. And in the spec refinement progress, it translates the natural language intent into partially formalized specification. And then spec validation validates this partial formal specification. If it is invalid, then it generates feedback and repeat the refinement loop. Otherwise, we put the valid partial formal specification into work list. And if work list has some refinement candidates, then we pop one of them and repeat the refinement loop. If work list has fully formalized specification, then now we get the formal specification. In this progress, we introduced two core ideas. First one is top-down spec synthesis, which is generates specification from high-level outline to low-level details. Second one is continuous spec validation, which checks partial specifications in the middle of top-down spec synthesis method. Let me introduce top-down spec synthesis first. From the work list, we pop the user intent exactly same with user-provided user intent. By using spec refinement tool, we translate this informally defined definition into formal definition like this. But here, undefined functions like valid posts and wipes alls are used. Instead of defining them informally at once, we define them informally. It means describe the functionality of these functions in natural language, not a formal language. By using this idea, we can reduce cognitive burden on large language model. We can reduce the cognitive burden on large language model compared to the monolithic methods. In the second iteration, same thing happens again. We pop the partially formalized specification from the work list and translate this into the formal specification. In the continuous spec validation, we can check this partially formalized specification is correct or not by using user-provided input-output example. By using this input-output example, we can ask this specification will accept this input-output example pairs by grounding this formal definition of the specification using user-provided example. Thanks to we have formal definition of valid post, so we can substitute this function call with this logical formula. And we don't have the formal definition of wipes all not now, so we encode this wipes all into uninterpreted function. And then put this logical formula into SNT solver like G3. Unfortunately, in this case, G3 said this logical formula is unsatisfiable because of wrong boundary condition of valid posts. So we generate feedback and repeat the refinement again. Now we get the corrected version of valid posts. So repeat the same things again, ground specification into logical formula, and ask G3 it is satisfiable. Then now G3 said this logical formula is satisfiable, so we can move on to the next iteration. In the continuous validation, we use 3 different types of validators. First one is syntax and type validators. It is straightforward. And second one is logical consistency validator. It checks specification is neither tautology nor contradictory. Third one is, we seen right before slide, input-output example consistency validator. It checks 2 aspects of specification. First one is spec accepts correct user-provided input-output examples, and second one is reject incorrect user-provided input-output examples. Now let's move on to the experiments part. We use 2 different types of benchmark. First one is algorithmic problem. It consists of human eval plus, and human eval plus consists of simple algorithmic tasks like implement sorting algorithm, and apps is composed of more complex algorithmic problems. And second one is real-world software benchmark. We use DefExpose, which is composed of known Java bugs in open source Java projects. And as a baseline, we use NL2 post-con, which is monolithic spec generation method using large language model. For large language model, we use GPT 4.1 mini with temperature 0.2. As an SMT solver, we use G3. Our first question is, can Expecto generate correct specification? In this experiment, we compare 3 different variants. First one comes from NL2 post-con. It trying to capture all constraints in the natural language specification. Second one is simple. It trying to capture only a single constraint from natural language description. And the last one is Expecto. Before getting into the detail, let me explain about the details of what is correct specification. First property is soundness. It is about rejecting incorrect input-output pairs, and completeness means specification accepts correct input-output pairs. So correct specification should satisfy both properties. So let's focus on the number of correct specifications. In the human level plus, Expecto generates 1.2 times, 1.4 times more specification compared to the baseline. And surprisingly, Expecto generates 2.1 times and 2.8 times more specification in more complex benchmark apps. So in conclusion, Expecto generates the most correct specification on both benchmark, and furthermore, it generates much more correct specification in complex benchmark. Second question is about, can Expecto detect real-world bugs? In this experiment, we checked Expecto-generated specification can detect known bugs in Java methods. Specifically, we provide Java document and buggy methods to Expecto and generate formal specification. Simultaneously, we run the unit test and collect input-output pairs. Here, input-output pair means that object state of corresponds Java method before executing the method and after executing the method. And put these input-output pairs to the formal specification, and we check does specification reject wrong input-output pairs. In this experiment, we use same variants and focus on the sound and complete specification. Here, Expecto generates 3 times to 7 times more sound and complete specification compared to the baseline. So we can conclude that Expecto can detect bugs using generated specification, and it means Expecto generated specification is as precise as enough precise to detect real-world bugs. So here's the summary. The problem is formal verification is really promising way, but the problem is writing formal specification is really challenging for ordinary programmers. So Expecto is the solution by converting natural language intent into formal specification. And we introduce 2 core ideas, top-down spec synthesis and continuous spec validation. Result, Expecto generates more sound and complete specification on algorithmic benchmark and real-world software benchmark as well. This is our homepage, and thank you for listening.
Hi. So I have a question about your specification and the idea of completeness and stuff. So what prevents me from just writing the program again?
Sorry, I didn't hear.
So imagine, assuming I can solve the problem, what prevents me from just writing the program, like the actual answer, again, as a specification? Your spec language is powerful enough. So for your wall example, right, you've pretty much given me a complete mathematical description of the problem. And the only difference between that and your actual solution is that your solution is like executable or something like that, right? So why can't I, like, imagine you gave me like something powerful enough, like, you know, the lean interface or whatever. I'll just model whatever your problem is, I'll get a complete solution, and that's my spec. How does your paradigm prevent me from doing something like that? Especially because you're talking about completeness, right? And I actually don't know what completeness means. When you have some generic, you just have some documentation, you have some code. I don't know what spec is most powerful. But given how you're evaluating completeness, I can just write this answer again and then I'll be done, right? So that's...
Theoretically, we can I think that is not a binary concept. I think it is some kind of gradual concept. So if we have more specified specification, then we can detect more bugs in the implementation, right? So we cannot say some specification is fully specified in practice. So I think that is some kind of gradual concept. So
can I beat your benchmark by just writing the answer again?
Yeah.
Will you allow me to do that?
Okay. Let me think about it more and.
Yeah, thank you for this work. I'm Shuvendu Lahiri. I'm from Microsoft Research and one of the authors of the Andrus et al. Paper. So thank you for doing this work. It's good to see the benchmark and the techniques being used. I can address Aditya's question offline about the completeness. My question was, when we did these formal specs, they were actually Java or Python expressions, right?
Mm-hmm.
So what I'm curious is, and we didn't have the test-based validation because we did not assume the tests are provided. We only had the natural language, right?
Mm-hmm.
So that's one difference. But my question is, for the Python and Java expressions, how did you get them to Z3? Did you have a DSL to convert them to Z3? Because it's not clear how you convert arbitrary Python or Java to Z3.
Basically, we use DSL for writing specification, and for Java, because we use our own DSL, so we cannot directly apply our DSL to detect bugs in Java methods. So we serialize previous states of the object before executing the method, and after executing the method into some kinds of JSON serialized states and put them into our specification.
Hi. Correct me if I'm wrong. So you're taking the natural language description, creating a high-level specification with some uninterpreted functions, and trying to solve each uninterpreted function, like, right? Is that correct? So I wanted to ask, let's say you have this, you're trying to solve this partial specifications, and then you're doing that one by one. How, what are the cases where you have tried to solve 3 partial specifications, and then you're trying to find out what the 4th function is, and then you realize that the entire spec from the beginning is incorrect, and if you had to go back and fix that from the beginning itself, and how did you solve that in case you encountered such scenarios?
Sorry, I didn't get the point.
So you're taking the natural language description, and
yes.
The first step is getting a modular specification, with some unrealized or uninterpreted functions, and the next refinement step is you're trying to find the actual function for those uninterpreted functions.
Yes.
Now you're doing that step by step. You may have 4 or 5 uninterpreted functions, and you're doing that step by step.
Yes.
Is what I understand. Now let's say you're done with 3 functions, and you're on the 4th function, and you realize that there is no function that satisfies your test, and you have to, and that the reason could be because your original the modular specification that you had, that itself could be wrong.
Yes.
And how did you go back and figure that out, and how did you solve that?
We didn't explain. I didn't explain about the details of searching strategy. Basically, we using these kinds of tree search methods. So we sampling multiple formal definition for one informal definition. So if some path is unpromising, then we prune out that path, and we keep the searching with the promising path. Okay.
Okay, well, on that note, let us thank our speaker again and go to lunch. We can just leave this all here.
Welcome. We're going to have 4 speakers. Our first talk is about state space estimation for DPOR-based model checkers, and the speaker will be Minjiang from the University of Illinois.
Hello? Hello? Okay. So good afternoon. I hope you all enjoy your lunch. I will be giving this talk on counting traces. This is a joint work with Mohammed, Bala, and Rupak from MPI, Uma Masih from National University of Singapore, and myself from UIUC. Okay, so let's start with this very simple concurrent program, which have 2 threads and 1 shared variable. The first thread just reads 3 times from variable x, and the second thread performs 1 read. And we know there are basically 4 possible schedules depending on the position of the read from the second thread. But at the same time, we know that the 4 possible schedules collapse into 1 program behavior because they are concurrent, they're independent and concurrent. Namely, all the read from the same initial value. And one popular way to reason about program execution equivalence is Mazurkiewicz equivalence, which basically identifies executions that differ only by commuting non-conflicting events. 2 events are non-conflicting or independent if they access different memory locations, or they are both read. A DPOR-based stateless model checker is an algorithm that systematically explores all the Mazurkiewicz classes induced by a concurrent program. The goal is to check whether any execution may fail a certain program assertion or run into deadlock or data race. Typically, DPOR-based model checkers guarantees to explore or cover all the Mazurkiewicz classes, which means that they explore at least 1 execution from each of the Mazurkiewicz class. So in practice, there are 2 questions that is specifically related to the model checking progress. The first question is basically how long does it take for my model checker to finish? I would like to know, does it worth it at all to run the model checker on a concurrent program? And if so, how much time I would like to allocate? The second question is that if I run my model checker for a fixed time budget, and it didn't finish, I would like to know at least how much of the search space is covered. Our approach to address the 2 questions is to look into this mathematical problem, which is a counting problem. The problem asks for a given program instance P with an execution bound, which means that we assume every execution can have at most B events. We want to count the number of different Mazurkiewicz classes induced by the program. So the rest of the talk is organized as the following. I will give a very lightweight discussion on the hardness result. Then I will be introducing our first estimator, which is designed on a DAG model. Then I will be talking about the second estimator, which is designed on the tree model. And finally, I will be discussing the experiment and the evaluation. So first, we want to understand how hard is a counting problem. And in the paper, we show that under the assumption of sequential consistency, the counting problem is hard, even for programs with purely read and write events. Namely, we show that for the exact counting problem is Sharpie complete, even when one of the number of threads or the number of locations is constant. And a more negative result we showed is that approximation is also hopeless. Namely, there is no polynomial time sub-exponential factor approximation exists for the counting problem unless p equals to np. And this result also directly rules out the possibility of nice randomized algorithms, such as an FP-RAS, unless RP equals to NP. So given the hardness, we sort of lower our ambition. Our approach to solve the problem is to design the first unbiased estimator to estimate the counting. An unbiased estimator is a randomized algorithm which outputs a random variable whose expected value is a correct count. And in principle, if we run this unbiased estimator for sufficiently many times, the estimate will converge into the right value. And our hope is that in practice, the number of times we need to run for it to converge is reasonable. So our intuition in designing these estimators is to organize the Mazukevich classes into nice graph models that we know how to estimate. So the first model we propose here is a DAG model. It is a very intuitive and almost naive model. Namely, for the very simple concurrent program on the left, we model it using the DAG on the right, where all the nodes represent Mazukevich classes of prefixes of executions. And the edges in the DAG model are simply thread decisions. Like the red edge here basically means that the next event of the first thread is scheduled. And any path from the root to sink in the DAG is isomorphic to a program execution. And the more important thing is that in this DAG, the sinks represent the maximum Mazukevich classes we want to count. So the next question is that how can we build an unbiased estimator to estimate the number of sinks of a given DAG? It turns out this is a solved problem by Leonard Pitt during his PhD at Harvard. So the algorithm is classic and simple. For a given inference to a DAG structure, what we need to do is to sample a random path from the root to one of the sink. Then the product of the ratio between the out degree and in degree along the path is going to be an unbiased estimation of the number of sinks in the DAG. But why is this algorithm usable on our DAG is not a trivial argument. We first need to argue that for a given program and this DAG model in our head, we will be able to sample a random path. In this case, it is actually simple because, as I said, every path in the DAG is isomorphic to a program execution. So to sample a random path, we just need to execute the program with some concurrency control, which allow you to proceed with one of the enabled thread at each time randomly. And as I mentioned, for the calculation uses the out degree and in degree of each node along the sampled path. So we also need to query the out degree and in degree in the program model. The out degree here is in some sense free because it is in the program model, it is just a number of enabled threads. The only question is that what is the number of in degrees along each of the node? And it turns out under the assumption of sequential consistency, we can query the in degree very effectively by maintaining a frontier of maximal event from each of the threads. So as a conclusion, to run Pitt's algorithm to draw one sample in this DAG model is going to take linear time and linear space. And this is our first unbiased estimator, but this is not enough for it to work in practice because this is just an unbiased estimator. We want to run the unbiased estimator for multiple times and hope that the value converges into the right value. And this means we expect the variance to be low. But unfortunately, this is very difficult. As we show it here with this simple program, we are just one thread read from a variable y, and another thread have n read from a variable x. The DAG estimator we propose here already results in exponential variance, while it only have one Mazukevich equivalence class. This also means that the relative variance is also exponential. It means that the estimation is now going to converge in exponentially many rounds. Okay, due to the time limit, I'm not going to discuss the example in detail, but what we think is the following. For this example, which only has one Mazukevich class, namely one sink, it already have exponential variance. If we can organize the Mazukevich traces into a tree structure, then we will have zero variance because a tree with one leaf is just a path. And it turns out there is this model, which is defined by the state-of-the-art depot model checker, which is trust. So trust is a model checker that is optimal and stateless. It is optimal in the sense that it never explores two Mazukevich class twice. So the search space of the trust algorithm is actually a tree. But it's important to notice that the search tree of trust is very different from the DAG model. In the sense, the first difference is that the edges here are not represent partial order decisions, namely like RF, like which write can this read be reading from, or coherence relation, like where I can put this write in between other writes. And any root to leave path in this tree is also no longer isomorphic to program executions, but they correspond to the trajectories of the algorithm's search procedure. And the only thing remains the same is that the number of leaves in this tree is still the number of maximal Mazurkiewicz classes we want to count. And to estimate the number of leaves for a given tree is a very classic program, and there is a very well-known algorithm by Knuth, which is we call the Knuth estimator. Many of you may have already realized that Pete's algorithm is just a generalization of Knuth's algorithm. It basically says that to estimate the number of leaves in a tree, I take a random path, and I take the product of the all degrees along the path. Okay, and this number is an unbiased estimate for the number of leaves. Then we need to argue why Knuth is usable on this trust tree. And the major difficulty or nuance is implementability. Knuth's algorithm requires us to be able to query, to sample a random path effectively. But this is not generally true for any search tree. The reason is that if the existence of the right subtree in this graph depends on the left subtree, we cannot really randomly sample a path without constructing the whole tree. But luckily, this is not the case for the trust search tree, because trust, as I mentioned, is stateless. Its exploration does not depend on its history. So it does not use exponentially many memory. Its exploration only needs the current stack. And the second thing we need to argue is that this tree is not in polynomial size of the program execution, and it's a classic result of the trust algorithm that the depth of the trust tree is at most in polynomial of the program bound. So to use Knuth's algorithm to draw one sample in this tree is still implementable in polynomial time. Okay, but unfortunately, even this tree can still be badly skewed. Namely, the variance can still be exponential for concurrent programs with only n plus 1 Mazurkiewicz classes. And this is a classic example which we call the hairbrush tree that is often referred to the people in statistics when they're trying to reduce the variance of the Knuth method. The lucky thing is just that the Knuth method is very popular, and there is an extensive study by people who are trying to reduce the variance. So we use this method called stochastic enumeration to reduce the variance. Okay, and evaluation is that we implement both of the estimators inside a Java model checker JMC. And the questions we want to answer in the evaluation are that how accurate are the estimates and what guidance can they provide about the model checking progress. We call our DAG estimator PASTER due to its Pete's algorithm, and we call the tree estimator TESTER. And the benchmarks we considered are standard concurrent data structures, such as a concurrent linked list, timestamp stack, and lower bound queues, etc. And as we count piece-right benchmarks and some synthetic stress test benchmarks. In total, we have 42 program instances in the program, and with 30 of them, we have the knowing the ground truth. And the first observation we have in the evaluation is that the DAG estimator almost never converges into a meaningful value for all of our program instances, no matter how long we run it. But on the other hand, our tree estimator tester has a better signal. So we run tester for 2-time budget, because this is our expected usage from us on our estimator. We run the estimator for a short time before we run the model checker to get an estimate. And we show that as a 1-minute estimate, 66% of the benchmarks, the estimation was accurate within the 80% to 120% bandwidth. And for the 5 minutes estimate, 75% of the benchmarks estimate was actually accurate. And then I also show some of the benchmarks which we do not know the knowing ground truth to see how can we use the estimate to interpret the timeouts. For example, there is a concurrent benchmark we tested called course list. And we run the model checker for 1 hour. The model checker timeout after explore around 1 million Mazukevich executions. And our estimator shows that the estimation was around 2 million. So even though our the model checker timeout under the time budget, we know that it covered around 50% of the search space, which gave me a level of confidence. But similarly, for the OPT list benchmark, the model checker again timeout after 1 hour after explored around 1 million benchmarks. But our estimator said that the total search space it has around e to the 8 many Mazukevich executions, which means that what we have explored in 1 hour is very minimal. It means that we have very low confidence of what we have checked in the program space. Okay, thank you.
We have time for some questions.
Mm-hmm.
Can't come.
Thank you for the nice talk and nice results. So in the early part of the talk, you introduced this DAG model, and you mentioned that the number of sinks is equal to the number of Mazurkiewicz traces.
Yeah.
I didn't follow why that was the case. So can you give me, is it a quick proof or a quick intuition for why that is true?
No, this is just by definition, right? We define the nodes in the DAG to be execution graphs or Mazurkiewicz classes. That's why it's a DAG, not a tree.
Mm-hmm.
Namely, if two different prefixes actually reach into the same Mazurkiewicz trace, they will converge.
Okay, thank you.
Yeah, thank you.
Any other questions?
Hi, thanks for the talk. So I'm not an expert in model checking, but from the things that I heard about trust, they do this thing where like old executions get revisited when you learn new information about possible reads from edges, which like isn't that a problem if you need to randomly sample the tree because you need to know about those revisiting things, which you only know if you explored other parts of the tree? Like it is stateless, but it does like, I mean, it has the state of like its current position in the tree, and then that still informs like future exploration across the tree.
No,
so I'm wondering if that's a problem.
So trust is stateless in the sense that it only needs the information on the current stack to get future explorations. It has a special condition called maximality condition or what, which means that you can determine whether to consider this new partial order purely depend on the current what you remembered on the current stack. You do not need to consider the other branches you have already explored, but you may need the information on the current stack. So in this trust tree, it means that you need you see that different passes have different lengths, right? Although the program executions all have the same length. And we are basically only sample random paths in this tree. And whether a certain, and at each step, whether you should consider a certain RF only depends on what you have seen on the current path. Yeah, revisiting, yeah, we have longer passes because we're doing revisiting, but it's part of the tree model.
Let's thank the speaker. So our next paper is fixed parameter tractable linearizability monitoring, and the talk will be given by Umang.
Okay, so I'm Umang, and this is joint work with Junghan Lee, who was an undergrad student, and this is part of the thesis that he did with me, and it follows after a previous paper that was also published at UPSLA last year. So what is this paper about? Oh. Yeah, so this paper is about this problem called linearizability monitoring, which effectively asks, you're given an execution of this kind, which is, you can think of it as an execution coming out of the implementation of a concurrent data structure, and you're required to check if you can come up with a linear sequence which sort of explains this. This problem as such is NP-hard because think about it, you have to really enumerate all possible interleavings of all the operations to be able to determine this answer. And so in this paper, we are trying to reinvestigate this complexity boundary. And we show that for a very large class of data structures, which pretty much cover most important data structures, you can actually refine this complexity boundary. And we show that, in fact, you can come up with algorithms that run in this sort of a complexity upper bound, which is something like a big function in K. Think of it as an exponential function in K. K is the number of processes in your history, and some polynomial in N. So this is, in some sense, better than a very vanilla NP hardness result. Okay, because if I just have NP hardness, the only thing that I can guess is that it may take exponential in the length of the history, and the result basically says that that's not the case. Which means that if you actually have a fixed number of threads, then the scalability is polynomial in the length of the history. Okay, so for those of you who may not know what linearizability is, here is an example. So this is a implementation of a hash map, and it is supposed to run across multiple clients. So there are three different functions that this data structure implements. And I don't think I have the time or the interest to go through the entire example, but the broad outline is that if there are multiple clients who are trying to invoke this different functions here, they may interleave in strange ways, and if your implementation is not careful, you will get some really, really weird answers. Okay, and as such, this is yet another concurrency error, but when it comes to data structures, one can actually specify a very nice property, and that's what linearizability is. So linearizability is a way to specify correctness of data structures, which are implemented in a concurrent manner. And it basically says that you first figure out what is the specification of your sequential implementation of the data structure, and then if you want to determine if your implementation or some particular execution is linearizable, you just check if that execution can be explained by certain points, and these points will now constitute a sequential run of the sequential specification. If you can manage to come up with such a sequence of events and which explains the behavior, that's when it is linearizable. And for the same reason, if you look at the second execution over there, it's not a linearizable implementation of a stack. It's not a linearizable execution of a stack. That's because the only way you can linearize these things is when you do push 1 and then you do push 2 and then you do pop 1, which is not a valid stack behavior. Okay, so roughly, linearizability of an implementation asks if all histories coming out of that implementation are linearizable, meaning you can always find a linear sequence that is equivalent to the concurrent history. So that's the definition of linearizability. And if you've been following any amount of work in PL conferences about linearizability, there's a lot of focus on the problem of verifying concurrent implementations, and it turns out to be a very difficult problem for a lot of reasons, including the fact that your specifications can be very complicated. And when you talk to people in the industry who actually build these data structures, they nonetheless go for a more practical take. They try to test these implementations, think of it as a very giant fuzzer that is testing these implementations. And as part of these testing, this testing, one has to effectively answer this question. You're given a history, and you want to check if that history is linearizable. So that is the monitoring problem that I'm looking at. As I said, the general problem of linearizability monitoring is an NP-hard problem. And this hardness result applies to very simple specifications like register specification. And very recently, there have been some works on coming up with restrictions on the kinds of histories that you have so that you can get polynomial time algorithms. But in general, if you don't have these restrictions, the problem cannot be solved in polynomial time. Right, so the question that we're trying to answer is, can we take another look at the complexity boundary? Meaning we're not trying to restrict the histories, but we're only trying to understand if I can come up with better algorithms than exponential time algorithms. Okay, so these are our results. We show that for a large class of data structures, which I'll soon talk about, you can actually solve this problem in FPT, which is an algorithm that runs in time f of k multiplied by some polynomial in n. K is the number of threads. And we show that, in fact, you can view all of these linearizability monitoring problems through a very simple unifying framework. And that framework is something that is a problem of over graphs, and that routinely comes up in very different PL problems, including static analysis. And we also implemented our algorithms and show that they also work very well in practice. I realize I've already spent 8 minutes just talking about the background. So that's our input. You have a history with you, and you're given a specification. Think of it as stacks or queues. And the history has n operations and k threads. And you're required to answer whether there is a linearization of this history that explains the behavior of the history. Okay, so let me first talk about this generic framework. So here one tries to look at this graph. I call this graph the frontier graph. So if I have a history like that, from there I can come up with this sort of a graph. The nodes of these graphs are sets of operations. These are ideals in the sense that every such set in this graph is downward closed with respect to some kind of partial order that I can infer from the history. And now, and the edges represent addition of one event. And the main reason why I want to formulate this problem using graph reachability is that if I look at that graph, it's exactly all the paths all the paths in the graph are exactly all the linearizations of the history that I have. And in particular, if I am looking to solve the linearizability problem, I just have to check if there is a path in this graph which belongs to my sequential specification. Right? So linearizability monitoring boils down to this problem. So you have a graph, and you want to check if there is a path in the graph that belongs to some language. So this is called the language reachability problem. And the most interesting aspect about linearizability is that unlike other similar problems in concurrency, the size of this graph is actually very nice. It is linear in n, the length of the execution, the number of operations, and it is exponential only in the number of threads or processes. And that happens because the histories that you get are effectively are something called interval partial orders. And based on my previous slide, it follows that if I can find a polynomial time algorithm for this language reachability problem, I will automatically get a FPT algorithm for linearizability monitoring. So that's the essence of the rest of the talk. So I'm going to try to find classes of data structures for which language reachability can be solved in polynomial time. All right, so the first class of data structures that satisfies this is order oblivious data types. And the definition is roughly the following. The definition says if you have a data structure is said to be order oblivious if whenever you take two legal sequential executions of the data structure and they are simply permutations of each other, then they both land in the same state. By state, I mean something like the internal state of the data structure. For example, over here, if you look at these two executions, they're both valid, and they're both permutations, and they both land into this common state where the element stored in the priority queue is just the singleton set 5. Okay, so that is why I call them order oblivious, and there are a lot of data structures that very naturally satisfy this restriction. And then we showed that we can also extend this definition and add other data structures like registers. And this is a very mild extension of this data structure. Alpha is some sort of a parameter. And it roughly says that, on top of them being permutations, they also have to, have the same behavior on some extra automaton that you have on the side. The theorem now that we have says that for this class of data structures, you can also solve linearizability monitoring in FPT time. So alpha is that extra parameter, n is the number of events or operations in your history, and k is the number of threads. And this is just some details about the algorithm, which I think I'll not talk about. But this algorithm is roughly some sort of a graph search algorithm. Okay. Yes. So the next class of data structures is context-free data structures, and stack is one such data structure. If you have ever encountered static analysis papers that talk about CFL reachability, the idea is pretty much the same. So if I look at a data structure like stack, it is definitely not an order oblivious data structure, which is the class that I talked about a little while ago. In fact, it is not alpha OODT no matter what alpha I pick. So what do we do? Well, we come up with a new class of data structures for which language reachability is nonetheless polynomial time solvable, and that's the class. So we call this CFL ADT class, and the formal definition roughly says that if you can come up with a grammar for your specification, then the data structure is a CFL ADT. So as an example, for the stack data type, this is the grammar. It says, it's the routine push pop specification, except that the grammar can have as many rules as the number of values in your history. Okay. So because the problem of CFL reachability on arbitrary graphs is solvable in cubic time, it follows that for this large class of data structures, linearizability monitoring is also solvable in FPT time, because the graph itself is fairly large this time. Okay, so we show that you can actually further improve this result for the specific class of stack data structure, for the stack data structure, and if you sort of carefully observe what are the constants and how large is the grammar and what is the shape of the grammar. So this is not so important. If you're interested, please go and look at the paper. That is the most interesting aspect of the talk. We also show that for the Q data structure, you can still solve this problem in FPT time. The reason why this is, so by the way, Q is this specification. I'm just describing the specification as a label transition system. Okay, and the labels on this, the sequences of this, the sequences that are admitted by this label transition system are constitute the Q specification. Okay, so this is the usual thing that you would anyway imagine. The reason why this is a big deal is because the problem of checking whether there is a path in the graph, which is according to the Q specification, for arbitrary graphs, this is an undecidable problem because it sort of very closely resembles reachability in Turing machines. Even for DAGs, for arbitrary DAGs, this is a NP-hard problem. So we need to do something else. Oh, the slides are GPT generated, and now it messed up the figure here. The core idea behind this algorithm is the following. It relies on this very simple algorithm for checking if a sequence is a queue sequence. Okay, so suppose I have a sequence of NQs and DQs, and I want to understand if it is actually a legal queue sequence. Here is a linear time streaming algorithm, except that you have 2 pointers. The way you're going to process the sequence is as follows. You'll maintain 2 pointers. One is the current pointer, which always advances 1 step at a time. And there is this other pointer front. It sort of lags behind, and it intuitively represents the front of the queue. So for example, in the beginning, both of them will be at the beginning. And then I will advance current to the point when I will first advance it to peak 1, and then I will advance it to NQ2, and then again peak 1, and so on. The reason I can advance curve so far is because the front is at a place where I have NQ'd 1. As soon as I DQ 1, I will have to advance front all the way until NQ2. And that represents, that is the way to update what is the current front of the queue. So this algorithm actually runs in linear time, but it uses 2 pointers. So you can actually formulate this algorithm as some sort of a rewriting relation. R is a relation on pairs of sequences, and it roughly represents the same algorithm. And the core lemma is that this rewrite relation is effectively going to give you the queue specification. All right. I don't think I should go into all this, but the point is that once you have this, once you have nailed down this rewriting relation that represents the queue specification, you can actually lift it and formulate an analogous problem for the entire frontier graph. And you can check membership in this relation in polynomial time. And that's why queue monitoring can also be performed in FPT time. Let me also talk about the evaluation aspects of the paper. So we looked at some very standard data structures that were publicly available, and we compared against previous tools that were also trying to solve this problem, but in a very vanilla manner, and also other tools that were trying to solve this problem under certain restrictions. And we showed that our tool does reasonably well, and it sort of grows not too bad as compared to the number of operations in the history. And with respect to when it comes to number of threads, the scalability is also not too bad. I think that is the end of the talk. We gave a unifying framework for linearizability monitoring algorithms, and we show that for a very large class of data structures, indeed, this bound applies. And we have a tool that is publicly available. So if you have any questions, I'd be happy to hear them.
We have time for one question while the next speaker sets up concurrently.
So can you give me an example where is there a common data structure that is actually whose monitoring problem is exponential in the history size?
Meaning it's not FPT?
Yeah.
So for example, there are data structures like DQ, for which we don't know the answer. I mean, we tried, but we couldn't solve it.
Okay.
Oh, sorry.
So our final speaker is going to talk about fast atomicity monitoring, and the speaker will be Yifan.
Hello? Yeah, okay. Okay, hello everyone. My name is Yifan, and this talk is about fast atomicity monitoring. So concurrency is everywhere for the modern software system, and concurrency bugs are also everywhere. According to a survey published on ASPLOS, about 65% of non-deadlock bugs of a concurrent program is atomicity violation. So here is a real example of atomicity violation in Masoko, and it has resurfaced for several times in the history. So basically, there are two different threads in this concurrent program. The thread one, both of the two threads, they actually try to access the field proc info. But the issue is that developers assume the statement S1 and S3 are executed automatically. But the issue is that the statement 2 in the thread T2 can be interleaved with S1 and S3. And this will cause a non-pointer dereference, which will crash the database. So atomicity may not be respected due to program's error. So how do we detect atomicity violations? We can use static analysis by scanning the source code of the program and just report if there's any violation in the source code. But the issue is that it has a lot of false positive. For a concurrent program, a false positive is really hard to verify and can be a huge waste of time. So the most popular method for detecting concurrency error is actually dynamic analysis. For the dynamic analysis, the checker will observe the execution generated by the program, and it will check if the observed execution violates the atomicity. So here is a trace generated by the concurrent program. A trace sigma is actually a sequence of events in a total order. We call that trace order. A transaction, it is a sequence of events in thread T, and it begins and ends with the small triangles. For example, here, the transaction T1, it actually have 2 events. And each transaction can be considered as an atomic block. We say that 2 events, E1 and E2, are conflict if they are in the same thread or they try to access the same variable X, and at least one of them is a write event. Or in another case, they try to acquire or release the same lock. So in this example, the event E3 and E4, which read and write on the variable X, are a pair of conflict events. So for the 2 events E1 and E2, we say that E1 conflict happens before E2 if first they are conflict events, and E1 appears before E2 in the trace. We use the arrow to represent the conflict happens before partial order. So a trace, it is serial if all events in transaction T are executed without interleaving with other transactions. So if we look into the first 2 traces, we can see that the transaction T1 and T2 are not interleaved with each other. But for the last trace, T1 overlaps with T2, so it is not a serial trace. A trace may not be serial, but it can behave as it is a serial trace. So we say that a trace is conflict serializable if we can reschedule the events of the trace to get a serial trace sigma prime, and the conflict happens before partial order remain the same to the original trace. So here is an example. The first trace, sigma 1, it is not a serial trace because you can see that the transaction T1, it overlaps with all the other transactions. But we can permutate the events and transactions to make sigma 1 into zero trace sigma 2. And all the conflict happens before partial order remain the same. So sigma 1, it is conflict serializable. If a trace it is conflict serializable, it means that there's no atomicity violation. So the problem is how to check if a trace sigma it is conflict serializable efficiently. To introduce the algorithm, we have to define the transaction happens before partial order. Given two events, E1 and E2, if E1 conflict happens before E2, then we say that the corresponding two transactions have the transactional happens before partial order. So if we look into the example, the E3 CHB E4, so the transaction T1 happens transactional happens before the transaction T2. And if a trace is not conflict serializable, it means that the transactional happens before partial order, it is irreflexive. The first paper trying to solve this problem is the Waldrom algorithm. And the idea is very trivial, actually. So it maintains a graph to represent the transactional happens before partial order. All the vertices correspond to transactions, and the edges represent the THB partial order. So if there are a pair of conflict events, and for example, in this example, E3 conflict happens before E4, so we just draw an edge from the transaction T1 to transaction T2. And similarly, because of the events E5 and E6, we draw an THB edge from T2 to T1. If there's a cycle in this conflict graph, then we say that this trace it is not conflict serializable. So the time complexity of this algorithm is n squared. It is very high because in practice, n is very large. And n here, it is the number of events in the trace. There are also several other papers trying to resolve this problem. And our algorithm is actually the fastest one. The time complexity is nk squared. Here, n is way smaller than, k is way smaller than the NVL. K is the number of threads, and NVL corresponds to the number of events, locations, and locks. We have to mention that the consumption of memory footprint is also very small, so that we can implement our algorithm in an online tool because of the very low overhead of time and space complexity. The key idea of this algorithm is that we maintain two data structure, which is called latest remote transaction and earliest local transaction. The latest remote transaction is, for example, the LRT T2, T3, it represents the latest transaction in T3 that can reach the transaction in T2. So here, the LRT T2, T3, it is the transaction T1 because it has an outgoing edge from T1 to the transaction T3 in the thread T2. The earliest local transaction is the earliest transaction in T2 that is reachable from the LRT. So in this example, the earliest transaction in T2, it is actually T3 because it's the first transaction reachable from the LRT, which is T1. The key lemma of our algorithm is that given two conflict events, E1 and E2 in two different threads, there are three conditions to detect a violation. So intuitively, the first condition will capture the THB edge from the thread T1 to T2, and the second and third condition will capture the THB edge from thread T2 to T1. So if all the three conditions are satisfied, it means that there's a cycle in the graph. So here's an example to illustrate how our algorithm work. The event E13 is a CHP immediate predecessor of E14. So the two events are actually the last two events in the trace. And the LRT T2, T3 is the transaction T1. The ERT T2, T3 is the transaction T3. And it appears before the transaction T5. So all the three conditions are satisfied, then a violation is detected, which is the cycle from T1, go through T3, T5, then back to T1. Our algorithm is based on lemma 2, and we find that recording LRT and ERT is very difficult. So we can maintain them approximately. We can update two vector clock from and to in the complexity of k square. We make sure that when the LRT is open, we always have the vector clock from equal to the LRT. And this should be sufficient for lemma 2 to find a automaticity violation. So the time complexity of the whole program is nk squared. So for the experiment, we implemented our algorithm in two frameworks. The first one is the offline framework for dynamic analysis in Java program. And we also implemented an online version in Thread Sanitizer. For the offline experiment, we compared our algorithm with all the other existing tools, and the result shows that our algorithm is actually way faster than the existing tool. For the online experiment, we actually adapt the instrumentation framework of Thread Sanitizer. Here, the data of TSAN, it's actually the time consumption for the data race detection algorithm. And for our algorithm, you can see that the time overhead is actually very small. It's only 1.3 times slower than Thread Sanitizer. For the memory overhead, it's actually can be omitted. Yeah. So the conclusion is that Autumn Sanitizer is faster than the other tools, and it has smaller memory footprint. It is the first online tool implemented in Thread Sanitizer to detect the automaticity violation, and the experimental result confirmed the practical impact. Yeah, thanks.
We have time for questions.
So probably a naive question. Why is it that transaction serializability is equivalent to no atomicity violation?
Yeah, it's actually a lemma borrowed from previous paper.
Oh.
Yeah.
So it's not an immediate thing?
Yeah.
No, I don't think that's what he asked. He's not contesting the lemma. He's saying atomicity violation and conflict serializability, though they may not be the same.
Sorry? Yeah.
There's a slide where, like before you get into the techniques, you said that atomicity violation is equal to serializability. Yeah, this one. The first statement.
That is true.
Yeah. So here I think it's the automaticity violation is by definition based on the conflict serializable.
So this is an implication.
Yeah.
Conflict serializability implies more.
Okay.
Yeah. So it's actually just an abstract property of all the transactional system.
So you would be given the trace, but you don't execute. You first serialize it, and then you guarantee there's no atomicity violation.
I think we could take this offline. But yeah, I mean, you may be confused by the equals, but I think it was error. It's an implication, yeah. Any other questions? I had a question. I was curious what is like the largest code this is scaled to in terms of number of threads, in terms of lines. It's unclear, at least from the talk.
Yeah. We illustrated that in the paper, around like 50 gigabytes of the traces in binary format, so it can be really huge. Yeah. Yeah, fixed point. The number of threads we can support. Actually, there's no exact upper bound, I think. Yeah.
How does it scale? So basically, how does it scale with a large number of threads? Like, how about traces with 56 threads versus traces with only 8 threads? Are they the same in your algorithm, or is the 56 threads traces much harder to process? This is a question.
Yeah, actually, we also tried to conduct the scalability experiment. We find that because the 56 goes to 128, it's actually a small number, so it doesn't change the performance that much.
Okay,
yeah.
I see.
Let's thank our speakers, and now we have a break for the next little bit.
Thanks. It's really cool result.
Yeah.
Excuse me.
You can go do it, Ryan. You got a good loud voice.
Wait, I can do it.
Never mind. Is this working fine? Yeah, it is. Okay, this is good because people stick it real close to them. Does anyone do karaoke here?
Test.
Don't worry, I won't. I just feel like mic control is a whole world of pain there. Okay. So I'm told Schwabe had a good joke for the opening of the concurrency session. I don't know who told him the joke at all. But he said, it's unfortunate they asked him to chair that session and another one at the same time. So I have to tell you, we also have a slight problem with the GPU session, which is we've been overbooked. We have too many talks. And so I'm going to have to ask all of the speakers to give their talks simultaneously for us. Okay, I think we're good. We're going to start here with a talk from Guido about Kuiper. So he's going to tell us a bit about how we might do very high assurance GPU programming. Anything else you'd like to say before we start? No?
Nope.
Maybe just go ahead and take it away.
All right, thank you. And you can hear me okay, right? All right, so thank you. Yes, I'm going to tell you about Kuiper. Kuiper is this new language for safe and verified GPU programming that we're building. And this is joint work with a bunch of people, as you can see. And special shout out to Bastian and Jonas, who are interns with us and helped develop most of this stuff. So since this is the first talk of the GPU session, I thought I'd start with describing the beast we're trying to tame. So what is a GPU? How exactly do they look like? So very briefly, a GPU is a massively parallel accelerator, which you can also call a coprocessor. It's something that is on your machine. It has its own compute, its own memory, but no autonomy. It's the CPU that decides when to run things on the GPU and copies memory back and forth from the GPU memory to normal CPU memory. And GPUs are very important these days because of high compute and LLMs and machine learning and all of this. And it's all about the flops and all about the watts. Like performance is the name of the game. Everyone tries to get the last bit of juice out of these things because they're also very expensive and consume a lot of energy, like Saman was saying this morning. And so when the CPU schedules something on the GPU, it launches something we call a kernel. And a kernel is something with a lot of structure. It has this execution hierarchy. So whenever a kernel is launched, it consists of something called a grid. And a grid is composed of a set of blocks, and each block is composed of a set of warps, and each warp is composed of a set of threads. And there's possibly millions of these threads, and they're all accessing possibly shared resources, and they're all running maybe simultaneously. And some of these can communicate and synchronize with each other. Some levels can, some levels cannot. So it's really complicated. At the same time, there's a memory hierarchy that sort of mimics the execution hierarchy. There's memories that are close to the threads and close to the blocks. And all of the details are very important when you want to get the final last bit of performance out of these things. So the programmers need fine-grained access to all of this. They need to be painfully aware of the hierarchy, the execution hierarchy or the memory hierarchy. So great, they sound a bit complicated. So how are they programmed? So you might have heard of a language called CUDA. What is CUDA like? So a bit of a spoiler, it's an extension of C++, but let's study the simplest matrix multiplication kernel that you can write. And matrix multiplication is something that very common to do on a GPU. So the simplest kernel you can write looks something like this. There is a kernel function, and then there's an invocation. And the kernel function up there, we can go through it. The kernel function is going to run, every thread is going to run the kernel function. And this is going to run potentially thousands of millions of times. What this kernel function is doing is, first it's computing its global ID in this whole hierarchy of a grid of blocks and threads. It's getting a unique ID. With that ID, it's computing I and j, which are the rows, the cell of the matrix C, where we're going to compute the product. And then there's just a loop going through the matrices A and B, computing the usual dot product of matrix multiplication, and then writing it out to C at the appropriate position, at row I, column j. And then to launch this kernel, there's this kernel invocation at the last line with the triple angle brackets. And we launch this function with a grid of m times n divided by 1024 blocks, each block having 1024 threads. And these are enough to fill the matrix and compute everything. So already here, there's many implicit assumptions. And this is not so trivial to convince yourself that this works. The first assumption is that A, B, and C all live in GPU memory already. These look like plain pointers, but they are not pointers to the CPU memory. They have to be already in GPU memory. The matrices have to have the proper dimensions. There's no check against that. They have to be stored in row major order, and that's evident from the way we're accessing them, if you just look at the indexing. And also, m times n has to be a multiple of 1024. Otherwise, there are going to be some cells that I'm not computing. Or I would have to round up and then do something on the edge, on the leftovers. So there's already a bit of trickiness in this very, very simple thing. And as you try to get the performance out of this, you need to use more and more complex features, like block shared memory and barriers to synchronize to use it. Vectorized memory accesses. You want to tile your matrices and then access them in strides. You want to access them in different ways. You want to use tensor cores, which are like tiny matrix multiplication units in the GPU. You want to do fusion, like do many things at once instead of going back and forth to memory. And you want to optimize the math. And as you might imagine, this is a bit of a recipe for disasters. So there's memory bugs that can happen very, very easily. There's data races when you're accessing the same data and modifying it. You can mess up the math, and it can be completely incorrect. And you can have undefined behavior if you're not satisfying the preconditions that some of these things have. Like the tensor cores have very precise preconditions. So it's not a great place to be in, especially if you're thinking of applying GPUs to machine learning, which everyone is doing, because you might never realize that you have a mistake. How would you even know? You just get some set of floating points, and maybe your algorithm doesn't work, and you don't know why. Maybe you just made a memory mistake. So naturally, the community, both the PL community and the industry, have been developing GPU languages or ways of making this problem go away. And there's lots and lots of languages. These are just a few, and Saman in the keynote this morning was mentioning many, many more. Some of them are even ML compilers, where you just describe a neural network and you just get the code out. You don't need to do much. But they fall in a classic trade-off between control and safety. And control is like what gives you performance. Control is what allows you to use every last drop of performance of the hardware. So exposing all of that in a safe way is not something that you can usually do. And most of these languages relinquish performance or are unsafe. It's usually that you cannot have both. So the point of this talk is that formal verification will enable safety and performance at once. So we're going to try to have our cake and eat it too. So enter Kuiper. Kuiper is this language for verified GPU programming. It's built on top of F-star and Pulse that you might know. So it has dependent types, a very fancy type system, and separation logic, a very composable way to reason about state. Every program you can write in Kuiper is safe and data race free. It's impossible to make a memory bug. And optionally, you can do full formal verification or full functional verification of the algorithms that you're writing. And it's also highly, highly polymorphic. And that's mainly what I'm going to be focusing on today. But it extracts a simple CUDA. There's no overhead in the code that you're generating. But you can write it at a very high level of abstraction. So in a way, you can also see it as a CUDA verifier, because anything that you can do in CUDA, you could potentially do in Kuiper and verify it and extract it. And this is more about the tool and the practical side. On the theory side, for those who know about separation logic and et cetera, some of the contributions to the paper are a model of heterogeneous CPU-GPU programming and separation logic, including reasoning about where resources live and how they can be accessed. There's a verified account of array views and tensors and layouts and all of the memory operations or memory representations, and some idealized reasoning about floating point that I will mention later today. So if we go back to this kernel, let's try to verify it. This is the kernel function that we just saw. And verifying this in separation logic, this is not too difficult, actually. We just need to figure out what we want to do. So one thing we can do is write it in Pulse. This is what the syntax looks like, and it's very much similar one-to-one translation to what you see there. There's one difference that I'm not computing the global ID. Instead, I'm getting it as an argument, which is a simplification that Kuiper gives you, but it's not essential. So here I'm taking the arrays that are of the proper size. This is statically checked. I'm taking my global ID, which is also a number between 0 and m times n, so I know I'm in scope. And then I do the same thing as I'm doing there. I compute I and j, I do a loop, and I write it out to C. Now, to verify this function, what you have to do is two things. The first one is state precisely what resources we're allowed to access. So the first thing is we state in the precondition of this function that we get read-only access to A and B, and that's what this thing means. And we also get full access, so mutable access, to one cell of the C array, only one cell. And our postcondition here says that, well, the precondition is that that cell pointed to anything, and my postcondition is that it points to the matrix multiplication of A and B in the relevant position. And the other thing I have to do to verify this function is add a loop invariant that explains why this is true. So once we have that, this function is accepted by Pulse and the Kuiper framework, and we can extract it to CUDA and get basically that code you see there, pretty much exactly the same. But what about the kernel call? This we haven't done anything about this thing. So how do we justify kernel calls as separation logic? Every thread of the kernel call, the way we're going to model it is that they all run potentially in parallel. Now, this is not exactly true of the hardware, but it's a novel approximation of the behaviors. So if you think of each thread as running, they each have the kernel function kf has a precondition and a postcondition parameterized by their ID. And it goes from pre-0 to post-0 and pre-1 to post-1 and etc. The way we can justify that this kernel invocation as a whole is multiplying the matrices is transform the high-level precondition that we have. We have ownership of all of the matrices, and we can explode them into read-only permission to A and B 1,000,000 times, and then explode the matrix C into pieces, and then give each of these to every kernel function. So there is a stage here that takes the top-level precondition, all of the resources you can access, and slices and dices them into the ones needed by each of the runs of the kernel function. And then the same thing happens in the other way around for the postcondition. Once you have all these separate postconditions of the threads, you can add them all up back into full ownership of the matrix C and also prove that it is the correct matrix multiplication. These proofs are usually pretty direct. They can get complicated, but for this kernel, they're very easy. For those who know about separation logic and etc., this looks like an iterated star, but it's something slightly different, actually. We came up with a new connective called for all plus, which is similar but nicer to use because it doesn't have any finiteness requirements. So you could ask me about that if you're interested. So once you have this, and I should say, we do this for every level of the hierarchy. So when you take your kernel and you split it into blocks, you do this technique. And then every block does the same thing to split into threads. And then we actually have not modeled warps in this thing at the moment, but it doesn't really matter. We would just add it in the same way. So with this, you get database freedom and memory safety because every thread is honest about what they can access and there's no illicit sharing. So once we have this, what we can do, given that we're in a very highly typed, highly expressively type dependent language, we can take that kernel function that we just had and we can put it in a record with its pre and post conditions. And we can take this setup and tear down proofs and just package them into the record. And then this record is just, it knows the size of the grid, it knows what function to execute, and it has proof of correctness of why this kernel as a whole is correct. And it just tells me what the pre and post condition are of the full kernel invocation. So I don't have to think about what each thread is doing. So then we can take that old function we had, package it into a record where we choose the pre and post conditions, we prove setup and tear down. And then we just have this package that when C points to something, it will turn it into C pointing to A times V. And then we can just launch it. We can just call it. There's no implicit preconditions anywhere. Everything is all encapsulated. Wow, okay, I'm going really slow. And you can even do this asynchronously. And then you can get exactly the same code we had before. Now, I don't want to do this for every kernel we have to write. You usually have many, many variants of kernels at different types, layouts, etc. So a big point of Kuiper is that kernels can be generalized first by types. You can use type classes to define a single kernel over a family of types. You can use higher order functions if you'd like. In this case, we'll use it to decide how to combine the old value of C with the new one, which is something that's usually done very commonly. So once you have the general version, you can do matmul by just projecting the second component. You can do gem by just saying, I'm going to combine the old and the new value with A and B, alpha and beta. And you can even fuse some function, point-wise function after the gem by just putting it there. And then when you do this with specialization and inlining, you get highly reusable zero-cost abstractions. All of this comes out, and it's just plain CUDA code that without any overhead. The higher order functions obviously do not exist. And this is nice, but we're still working with flat arrays, and we need to do this indexing that gets really tedious. And if you were not in a verified tool, it's a source of bugs. Here, it's just tedious, and it's really awful to use. So the only reason we're doing this indexing is because we're trying to map this two-dimensional object into memory. And you can choose that mapping, and there's the row major mapping. And that's one choice, but there's many more choices. This choice is just saying that the cell ij goes to that position in the array. So to generalize all this, we developed a general theory of arrays that allows you to define these virtual arrays that have any index type, any virtual type, like this matrix up here. That's the way I view the array. And any injection into memory. You get to decide exactly how everything is laid out. You can have holes. You can go backwards. It just has to be an injection. And it's all fully foundational and verified in separation logic. And it allows you to do things like, if you had this other matrix, it happens to be the transpose, if you were to store that matrix in column major format into memory, the memory is exactly the same. So this theory allows you to do view transformations where you just reinterpret one as the other at no cost. This just happens. It's just a proof step, and nothing happens in memory. And this generalizes to tensors of arbitrary rank. You can do tiling. You can take slices of matrices. All of this is supported uniformly. And what's even nicer, it allows you to use bidimensional accessing on these arrays and just state the layout on the type of the array, and everything is just worked out for you. And then you can change the layout with just a one-line change if you want a separate version. Or even better, you can just make it completely polymorphic on the layout because you're in a very dependently typed language. And this is if you're getting bang conflicts with the layout, you can just switch it with like nothing. And every gem we wrote is layout polymorphic. So yeah, and then you can get the row major version, you can get the column major version, and you can get every combination that you like, all for free. You verified it only once. So yeah, I kept saying we're doing verification, functional verification, floating point. So floating point. When we say floating point and functional verification, what does it mean? Is there even a correct result on floating point? Because floating point is very complicated, right? Associativity doesn't hold. If I take x plus y and subtract y, that's not necessarily x. So one way of fixing this is fixing reduction order everywhere. I'm saying the specification could say, I'm adding the matrices elements in this way. But then as soon as you change it, it's a different spec, and there's no reuse. So what we do is we have this abstract notion of approximation that allows you to relate a floating point number to a real, and you can only construct homomorphically by rules such as the one you see there. And it allows you to essentially prove algebraic correctness, completely ignoring numerical error. So we don't prove numerical error at all, not yet at least. But I see this kind of as a feature instead of a limitation, because all of these specs are completely compositional. While if you're doing concrete error bounds, that's a much harder problem that we don't necessarily want to do yet. So the specs look more like this. The result is just a correct approximation of the result. And with the higher order and et cetera, this allows you to do things like, if I want to take the gem from before and numerically stabilize it by using something like k-on summation, which you might know or you might not know, but it's not too relevant, there's just a higher order combinator here that implements k-on compensation for any sum. It just tell me what it needs to add up, and it will just do it for you and compensate it. And then I can take that old kernel I had, change one line, maybe 2 lines, and now I get a k-on compensated version that's much more numerically stable. And the functional proof is unaffected. I don't have to fix anything else. So these are the main features I wanted to tell you about. So what have we done with Kuiper? Let me tell you a bit about evaluation. Yes. About performance. So the first thing, I claim there's no overhead. This is you can look at the performance part. This is mostly true. We do not find performance difference. We have very performant kernels that we don't yet reach like state-of-the-art super optimized kubeless in some settings. We've done a major many things. Many things are coming: sparsity, attention, LLM pipelines. There's more in the paper. If you're curious, please read it. My main takeaway for you here is safe, verified, high-order performance GPU programming is possible. We don't have to make compromises. This is a full-blown GPU, CPU language. So maybe Lambda is the ultimate GPU language. And consider using it, especially if your agents are doing the coding, which is something we should be scared about. So yeah, thank you, and happy to take any questions.
Thank you. Okay, looks like we got a couple questions here. Manya, if you want to come up and start.
It seems somehow too easy that you just introduced a magic backslash sim or whatever it is in LaTeX operator to capture floating point stuff. What is the semantics of that operator?
Of the approximation relation?
Yeah.
Yeah, so this is a good point. There is none. It's fully abstract and it's not defined. And there's this thing. It cannot be defined. F-star does not expose, or the Kuiper formalization does not expose real bit level details of the floating points. You cannot reason about it. If you could reason about it, I think you could prove this relation to explode it and prove that it's trivial. But since the floating point numbers are also abstract, you cannot, and you can only work with it with these rules. So it's more of a meta argument that this relation is meaningful.
So maybe you could prove some kind of useful soundness property using logical relations or something, treating that as an abstract type.
Maybe.
But it would be very interesting to see what that property actually looks like.
Yep.
Okay,
Yep.
future work. Thanks.
Thanks.
Okay, 1 second.
Hi. I'm not sure if I have misunderstood, but it looks like you're doing verification.
Can you speak up, sorry?
It looks like you're doing verification at the source level, but the compiler can transform your program in different ways. So is there a compiler that also respects these predicates while transforming your code from source level to the assembly?
So I'm not sure I heard it correctly, but the compiler and NVCC is allowed to transform things, but we're just assuming that NVCC is doing the right thing. If NVCC is introducing a bug, then yeah, that's out of scope. Okay.
Okay. Let me check real quick. I think we're going to stop at 2 questions. Apologies to anyone there. Just make sure we stay on schedule. Let's give Guido another round of applause.
Thank you.
And our next speaker is Manya Bansal. This is one of the PLDI distinguished papers. Oh boy! So no pressure on you at all, Manya. Yeah, exactly. Yeah. Well, it's a nice social construct to receive. Anyway, I think we are about ready. Anyone else hear any good jokes lately? No? Okay. All good? Okay.
Okay. Is this on?
Let's see. Maybe we need to hit the, yeah, it needs to be. There you go.
Okay, awesome.
Awesome. Please take it away.
Thank you. Okay, awesome. So I'm Manya, and today I'm going to be talking about our work that enables you to write low-level and modular programs for the GPU. Before I start, I want to give a quick refresher on GPUs. So on a GPU, execution happens thousands of threads at a time. It's a massively parallel architecture. And the most popular way to program GPUs is to use CUDA. In CUDA, you control the machine by defining the behavior of a single thread. So let's see what this actually means in practice. We're going to multiply a matrix, again, multiply A and B, compute output into C. And the way that we're going to do it is we're going to read the global thread ID, more about how we're going to compute this later, and this is going to be different across all of the threads. Using this different value, we will basically write something that looks like a parallel for loop if you've seen it in other programming paradigms. And using that, we can actually distribute the entire computation. Now, internally, the GPU is actually organized in a hierarchy. So there's a single thread, which is the smallest unit of sequential control. There's a warp, which is a group of 32 threads. Instructions are issued 32 threads at a time, and they execute in lockstep. A block contains a configurable number of warps, a grid, a configurable number of blocks. And this hierarchy is not only useful to logically organize your computation, but rather has meaning. Certain operations are only meaningful when executed at certain parts of the hierarchy. So an example of this is the tensor core operation. On the Ampere generation, a warp level of the hierarchy is the level of the hierarchy where you can go and execute this operation. And this is where most of our compute lives. So we really care about this. Let's see how we can program this in CUDA now. Like before, we have a function. Each thread is going to be executing its own copy of the function. It's going to locate itself by reading an ID. After doing that, because we're now going to execute a warp level operation, 32 threads, we're going to have this if statement, read the inputs to this operation, perform the actual operation, then finally write the outputs, and then synchronize all threads in the warp to make sure every thread has like sort of basically gotten to that point. The thing I want to highlight is that if I had made a minor mistake, so instead of 32 threads, I had written 31 threads, well then this tensor core operation would have actually been undefined. Worse still, that sync warp would have actually deadlocked our entire machine. It's going to wait for 32 threads or a warp's worth of thread to get there. That's not going to happen, so we're just going to hang. And you know, this is actually kind of okay, at least it's in the same function implementation. But actually, this can totally happen in the context in which you can invoke that function. So if the outer context doesn't realize that the inner function is going to try and perform this collective operation, you're stuck. So basically, all is well and good in CUDA until you're actually doing writing programs that are data parallel over threads. And all hell breaks loose when threads need to collaborate. And the situation is a little bit worse still, because I showed you two functions. I showed you a warp function, and I showed you a grid function. And they need to be called differently in different contexts. The issue is, looking at their interfaces, I actually cannot tell this difference. And so modularity fundamentally is broken in the CUDA programming model. In fact, I want to argue that the ecosystem reflects this lack of modularity. Many libraries, like the ones on the screen, can only allow you to control the entire machine at once. So they can't even be composed with anything else. But those libraries, like Cub, that actually do try to introduce finer-grained interfaces, actually expose that assumption in their names. And this should really send a shiver down everybody's spine here, because names are just names. They can't be checked or enforced. And you may be wondering, well, Manya, I've heard about like the N million GPU languages. What about any of those? Let's take Triton as an example, which is a block-level programming language. In Cub, we at least had 3 options. In Triton, we only have 1. So we actually don't need to make a choice because we don't have any. And this is great until you actually want to perform a warp group level tensor core operation. Well, in this case, you would want my presentation to keep presenting. Let's see.
It's a very dramatic surprise.
Yeah, it's a dramatic problem. Yeah, in that case, literally all does go dark, in that you basically rely on the compiler to figure out what's going on. So actually, Triton has introduced this lower-level programming model called gluon, and then basically gluon is the thing that we need to use to program this machine now. So you may be wondering then, well, Manya, I can see you're going to propose a language. What level of the hierarchy are you planning on choosing? And I think this is a general question that current GPU programming languages ask of themselves. At what abstraction should they expose the machine so that they can still continue sort of providing modularity without sacrificing performance? And I think this is the wrong question to ask. In this talk, I want to propose a different question. I want to ask, how do we give access to the lowest level interfaces on this machine without sacrificing modularity? And I answer this question by proposing a language called Prism. So Prism is a low-level GPU language that tracks in its type system how code is going to be using hardware resources. Using this tracking, it checks at function invocation time that the function is only being called if those hardware resources are actually available. The core idea at the heart of Prism is this idea of a perspective. A perspective is simply the view of the hierarchy from which we're going to be defining the machine's behavior. Let's see what this actually means. So in our simple tensor core example, we could actually already see perspectives in play. So that first statement there is a thread perspective statement. Literally every thread even has different values for that x variable. The next if statement, a warp perspective. The next 2 register-based loads are thread perspective. The tensor core, of course, requires the entire warp, a warp perspective statement. Same for those threads. And then finally, the sync warp, also a collective operation from the perspective of a warp. Given this intuition, let's operationalize our definition of a perspective. So a perspective is simply a level, a grid, a block, or a thread, coupled with a static constant. So a thread 1 perspective is simply a single thread. A thread 32 perspective is a perspective that contains 32 threads. A grid 1 perspective is single grid. In Prism, perspectives are aligned by default. No worries if you don't know what that is about GPU programming, but for all the experts, in the room, that means thread 32 perspective is always aligned and therefore always maps to a warp. So if we go back to the original program now, we can annotate with this program with the perspectives through thread 1 perspective statement, the thread 32 perspective if statement, thread 1 loads, thread 32 tensor core invocation, thread 1 stores, and thread 32 sync warp. Now the question that is sort of really important for us to answer is that how do we actually ensure that the perspectives we've actually annotated in the program are respected? And for this, Prism basically exposes them in the program source. So let's actually take this program and try to rewrite it in Prism. The first thing we have to deal with is that if statement, because depending on that if statement, our collective operations are going to be valid or invalid. The first construct then that I want to introduce is this construct of a split. A split statement basically helps you shard your compute resources into different parallel pieces. So each arm of that split is going to execute in parallel, and then that tensor core operation is valid because it lies in that scope of that thread 32 split. Now, this is not the only way you might want to shard your compute resources. So we have another construct called group, which basically takes a perspective and replicates its body across that perspective. So in this way, it kind of forks off multiple copies of that perspective executing that same code. Now, group and split attempt to make a certain promise to their programmers. They say, in our scope, the compute resources are going to remain logically coherent. So in that scope, there's always going to be 32 threads executing that computation. Actually, as it stands, I can make it so that this is not true. So if I just look at that x variable that contains different values and just simply branch using that value, well, then the tensor core operation is in trouble. That's going to be undefined behavior now. And in general, this is going to be a problem for us because you can use divergence on data to induce divergence on compute. And the way we solve this on Prism is that we actually track divergence on data so that it cannot induce untracked divergence on compute. So only groups and splits can induce divergence on compute. Let me show you what this means. So if we go back now to our original example, well, that data x simply lives at another perspective. That's a thread 1 perspective variable, which is to say it changes at the frequency of thread 1. Now, if I had instead tried to branch on the value of the thread 1, that's a compile time error. My compiler is going to scream at me because I actually cannot read that data. Let's dig a little bit deeper into the rules for reading and writing into data in Prism. So if I had a variable x here, like the thread 1 perspective variable, changes at the frequency of thread 1. And if I had another variable y, which changes at the frequency of thread 2, so it changes at most at the frequency of thread 2, then is it OK if I try to write the value of y into x? Well, let's try doing that. And this turns out is actually totally OK, because that x variable continues to meet its contract of changing at frequency thread 1. It's just a contract that sets sort of the upper bound on how often it can change. So this is totally fine. However, if I just sort of reset this operation now, and then try to write the value of x into y, well, then I'm in trouble. I've actually violated the contract that y sets up for itself. In general, data can read from broader perspectives, but broader perspectives cannot write into narrower perspectives. With this in mind, we can continue converting the other data into our program into this perspective form. So x now is a variable that lives at thread 1 perspective. We can also change our registers. And we can also change the actual function interface a little bit. Now, I do want to point out that that's a memory operation. And so we'll talk about this a little bit. But just to understand what that actually at thread 32 is doing, it's just saying that the value of that pointer for each of those threads in the group of 32 threads is exactly the same. It says they're sort of converged on that value currently. Now, since I allow reading from broader perspectives, I can simply now convert that read from the broader perspective into the narrow perspective, but I still somehow need to handle writing into that memory. Well, for that, we have another construct called partition. Partition basically takes in memory that lives at a broader perspective, lowers it to a smaller perspective, so that thread 1 perspective, and in doing so, basically takes a function that helps us do this and introduces a new name. So cthread value is now going to be different for the body of that partition based on the function that we actually give it. So every time you index into cthread now, it's going to automatically be indexed off of that function. Again, you might have noticed I've actually not fully grappled with the true memory hierarchy on the GPU. I've not talked about shared memory, global memory, and so on. Basically, this is like a can of worms that we do completely handle in the paper, so I would recommend reading it. In fact, a lot of people who presented right before me have awesome work handling this. So for more details on memory, you should read the paper, but it's basically almost a direct analog on how we handle compute. Last piece is now the core piece is how do we actually call these collective functions. So turns out, every function in Prism carries a requirement with it. And we check the body of each function against that requirement. So now, when we actually want to call these collective operations, they're simple function calls. And we can actually check the fact that we meet the requirements because their interfaces tell us what their requirements are. And in this way, we get modularity. We also implement some pretty popular intrinsics within the compiler itself, so user code doesn't need to add it, but you can very well do that. Now, everything that I've talked about in Prism has been formalized in this core calculus that statically tracks perspective on code and data. A lot of ideas in this calculus are borrowed from dependency tracking. So we basically use dependency tracking to make claims about how data from broader perspective cannot flow into data located at a narrower perspective. Using this, we prove a soundness theorem that says that programmers can never execute operations for which they lack the correct perspective. Again, more details in the paper. Finally, we test whether Prism can actually perform speed of light computations. To do this, first we implement the single pass prefix scan algorithm with decoupled lookback. Here's a really scary picture to intimidate everybody. No need to understand this, but the upshot here is that the convergence and divergence that you see in this picture is actually fundamentally different from the ones in dense tensor programming. So basically, Prism can express a lot of variance, and we can match speed of light performance against existing libraries. Again, we also implement the quintessential matrix multiplication example as in an asynchronous pipelined warp specialized calling into tensor core for the H100, and we benchmark against the cuBLAS library. There's a 10% difference, not because Prism can't express something, but rather a compiler pass that triggers in cuBLAS does not actually trigger in Prism. Ask me a question if you're interested. But hopefully at this point, I've convinced you that Prism is a low-level modular GPU programming language, and I'm happy to answer any questions that you might have.
Thanks for the talk and sharing your perspective.
Thank you.
Go ahead and take the first question.
Thank you, Hank from UIUC. I have a question that there are, in modern GPU programming, there are certain cases that asynchronous tasks are, for the entire block or the WAP is initiated by one single thread.
Yes.
How can Prism check and model and check that?
Yes.
Thanks.
So Prism does totally handle it. But I want to also be clear. So the kind of memory guarantees that we actually provide in Prism are not data race freedom or anything like that. Actually, in Prism, we allow bounded data races. And there's a lot of detail in the paper. But the H100 example that I showed you took advantage of TMA loads and stores to actually do warp specialization and load up data. Otherwise, it's impossible to get the kind of performance that we got. But the way that it works is that similar to Split, where we have sort of a sharding of resources on compute, we have an operation called claim that helps you sort of shard a piece of memory across two competing, compute resources. And using that operation, we can prove a bunch of things about asynchronous data movement. Yeah.
Thank you.
Do we have any other questions? Okay, I'm going to take one from someone who can't ask her at the lab later. Sorry, David.
Just a quick, simple question. Gaxiang from Columbia University. So, do you prove the semantic, the functional of semantic equivalence between your Prism code to the lower level CUDA, or not?
I mean, so the thing that we prove is that the type system, it's like the normal syntax operational semantics equivalence. The operational semantics that we model, we don't we do so with a good faith model of the actual machine. But the actual operational semantics that we claim, we assume that they are faithfully modeling the machine.
If we have a third question, we can take it. I'll take it in the back here while we're changing over. Pardon. Give me a second, Sri.
Hi. Shripati Pai from the University of Rochester. So this has been a problem since CUDA 1, so this is a really nice approach. I still don't think that a programmer should decide how work is divided among the warps and threads. So do you plan to do some sort of inference, like you're calling this from this perspective, so as to choose between these functions that have been provided by the programmer or something like that?
So this is a really good question, and I think this goes to something like I believe at my core, at least currently, which is that to actually write speed of light performant GPU code, you need to give programmers ultimate control. And let me give you an example of a scenario where this is actually necessary. So in the hopper, the way that you actually write a speed of light warp specialized matrix multiplication is that in your producer warps, you at like runtime dynamically give up registers. This is like an absurd thing to do, and any compiler writer would like, yeah, this is like a crazy thing from the perspective of a compiler writer. So I don't think, at least GPU architecture stabilize enough that we know all of these tricks, which I don't know, I think oftentimes even for CPUs we're handwriting code, but certainly for GPUs, architectures as they stand today, it's kind of impossible to for a compiler or like an automatic machine to come up with all these tricks without having seen it in the first place. So yeah.
Okay, I completely disagree with you, but I have no
Let's definitely argue about this. Yeah.
Well, sounds like a wonderful argument to have in the break, but for now we have another wonderful speaker who's getting the audio set up. Pardon me a second. Okay. So.
Yeah, okay.
All good, Sumik?
Audible? Am I audible? No. Okay.
Audible. Great.
Yeah, audible.
Okay. So Sumik will tell us about handling streams on GPUs a bit. Should be exciting. Take it away.
Thank you. So, okay. So we have, as of now, we have seen a lot of CUDA programs. I won't go into the details of that how the GPU programs even work. You already know the basic ideas. But you know about how the GPU kernel programming or multi-thread programming actually works. But you need to see the CPU programming side as well. So this is a typical CUDA C++ program that is being written. I will go in very brief. This is the CPU part. The CPU initializes the data, followed by the data transfer from CPU memory to the GPU memory, followed by the GPU kernel launch. We do not care about the kernel code as of now. I'm not showing that kernel code. And you ultimately copy the result back from GPU memory to the CPU memory. Now, part of the scary program. Again, matrix will come. So this is a matrix vector transpose program taken from Polybench MVT. If you see that all these CUDA operations here are launched on the default stream and they are synchronous in nature. What do I mean by that? Let's see a timeline diagram. So these host to device transfers will be executed first, followed by the kernel 1, then followed by the kernel 2, then followed by the D2H. If you see here that all of these operations are waiting for its previous operations to completely finish. Now, is this even necessary? The answer might not be yes. If you see that at line number 5, CUDA memcopy is writing to X2 GPU, whereas MVT kernel is not even accessing that data array. Similarly, for this line number 7 and line number 9, there is no dependency. Well, these two kernels, you may seem that they are dependent because of the A GPU, but let me tell that those are being read in both of the kernels, so there is no dependency. Further, if you see between the line number 11 and line number 14, there is also no data dependency. So provided this information, do we really need to serialize the operations on the CPU side and not following the serial order? Can we improve the performance? Well, the answer is yes. I will show the performance, but see the transformed program which will give you the performance. Here, all the CUDA-mem copies have been transformed into CUDA-mem copy async, and they are given to different streams. We have not talked about stream so far. What is a stream? Stream is a queue of multiple CUDA operations, where if you launch different CUDA operations in a single streamed program, it will be executed in the serialized fashion. If you use two streams, what will happen that you can have parallelism between the multiple CUDA operations as well. Notice that I'm talking about the operations from the CPU perspective. We are not talking about the GPU kernel's perspectives. So here, OP1 and OP2 are independent. They can be launched independently, and same with the other operations. So if you see here that MVT kernel 6 was not dependent on line number 5 and line number 7, so they are not provided the same stream so that they can run in parallel. But line number 13, MVT kernel 1, still depends on the rest of the CUDA-mem copy host to device operations, so you need to do stream synchronizations. So if you see that line number 9 to 11, there are stream synchronizations. 15 to 17, there are again stream synchronizations for the same. So if I show you the timeline diagram of this transformed program, the kernel 1 now does not wait for the H2D to finish, kernel 2 same does not wait for kernel 1 to finish, D2H operations or device to host operations does not even wait for kernel 2 to finish. And this gives us a massive performance improvement over the baseline program. Now, is this even optimization relevant in the real world codes? You can just say that, okay, I will just manually write the optimizations. What is that? We have studied top 10 most forked CUDA C++ projects on GitHub, and we have found multiple GitHub issues following from synchronous ones to asynchronous API calls. Someone has put incorrect stream allocation to API calls, potentially limiting the overall parallelism, and someone has put a wrong synchronization barrier or has put a synchronization barrier at suboptimal program point, so it is limiting the overall parallelism. So we are saying that, okay, manually allocation of streams to API calls is error prone and it needs automated support. We are providing our technique streamalloc, which is an automatic framework to assign the streams and stream synchronizations to the CUDA API calls. The first one is a read-write analysis. I will go very brief. We all know about this, but so if you see the call graph here, that the main function is calling the kernel, the kernel is calling the foo function. Now, if we see here that a GPU array is being written inside the foo function, we need this information to be passed at this line number 10 so that the later stages of our analysis understands that these arrays have been read and written without analyzing the function body again and again. Similarly, for the reads also, it performs a compositional bottom-up analysis to find out the read and writes at the call sites. Now, coming to the next part, which is the CRA analysis, which we talk about the can run asynchronously analysis. We will show the CRA analysis in the form of the control flow graph of the same program. It performs a top-down intra-procedural analysis, creates a dependency graph to identify which operations can run asynchronously to which other. So there are 3 different CUDA operations, L3, L7, and L9. We will be inserting all of them inside the dependency graph. Now, if you see here that L9 is dependent on L3, we found out via the data flow analysis. I'm not showing it here. More details are in the paper. Then L9 is also dependent on L7, But if you see here that via this package, L7 is also dependent on L9. So you have to put this edge in the dependency graph. Now, from this control flow graph, we have this dependency graph. Unlike the traditional read-write analysis, which collects all the writes that reach a read, CRA only cares about the most recent accesses. Because if one read, like for example here, like node B is reading B and node A is reading B, and node B is reading V, node C is writing to V. Now here, we don't care about the dependency from A to C, because by the time B is executed, A is already finished by means of the same stream or stream synchronizations. Now we have the dependency graph. How to assign the stream identifiers for each of the nodes in the dependency graph? We come to the DFSA algorithm for that, but before that, remember that our goal is to assign stream identifiers to each node in the dependency graph, such that the independent operations can run asynchronously to each other and achieve parallelism. One can argue that there can be a naive approach that each node in the dependency graph should be assigned a unique stream while synchronizing on its parent node, because parents are on parents the childs are dependent. Well, it works perfectly fine in this case. If you see that all three nodes have been given different streams, L3 is synchronizing on its parent node stream, L1 and L2 are not even dependent and they can run parallel to each other. But this does not work in every case. Say example for a linear chain of dependencies, where in the program order, L2 will be executing after L1 and so on and so forth up to Ln. Here only one stream would have done the whole job, but we are giving n number of streams with n minus 1's number of synchronizations. That's a massive overkill. Streams are not free, by the way. But that is not the only case. The number of streams is not the only case. If you see here, all of them are getting the different streams with the proper stream synchronizations. L12 gets executed after L11. But L10 and L12 are independent. However, this stream synchronizations here is ensuring L10 should finish before L12 gets even launched. So this stream assignment creates a spurious dependency between the L10 to L12. Just a simple resolution. Can we solve this by keeping the stream of every child the same of its parent? Well, it gets solved in these cases. However, consider this case. L21 and L22 are the childs of a single parent. If you give them the same stream identifier as that of the parent, they won't even run in parallel because you have a spurious dependency by giving the same stream. Okay, how about assigning the same stream as that of a parent in case of a single child and assigning different stream in case of more than one child? We have seen that this works, but there are some more tweaks to happen. For example, care about this dependency graph. Here, every parent have only one child, and so if you give them the same stream, so here you'll say that, okay, this is perfect. The problem is, if you revisualize the dependency graph in case of the program order, see that L3 and L7 are not even dependent, but L7 can execute after L3. It is not even executing after L9. So what should we do? We need a new approach for this. So that's why we gave the DFSA algorithm, data flow based stream assignment. We start from the start node of the CFG, comes to this one, L3. Now we have the color, notion of the color here. If a node in the dependency graph does not have a color, it can have from two cases, either from its parent or it can generate a new color. Here, L3 does not have any parent, so it will be generating a new color. Just a question, just a clarification that we introduce colors as so it will be visually appealing. You can think about anything like IDs and all, they work the same. Now if you go to the L7, L7 does have a parent, but the parent itself does not have a color. So you give a new color to it. Come to L9, L9 also does not have a color, but it can inherit the colors from both of its parents. Now, via the backage, you have to come back to the L7. And if you see that, now its parent have a distinct color or different color from its own. So it will try to inherit its parent's color as well, making both of its parents and its own colors same. And if you just familiar with the data flow analysis, the algorithm will go again via the backage, but it will come after some time to a termination, and we are stuck with these colors. Now, the idea is very simple. Same colors will get the same stream identifiers. So color 1 is getting same stream. Color 1, 2 is getting the different streams. And every node will be synchronizing on its parent node. Now, L7 has a parent node, but they have the same stream identifiers. So here the stream sync is none. Now, L9 have a parent who have a different stream identifier than of its own. So we give the stream synchronization as 1. Coming back to the motivating example, this is this graph we have got from the compiler framework of ours. And we have given these stream synchronizations and streams. Finally, after the streams and stream synchronizations, we are going to the automatic transformation phase by our compiler. So the compiler will take the LLVM IR and it will be transforming the code. For example, here the CUDA copy in the IR has been transformed into CUDA copy async with appropriate streams and stream synchronizations. So if you see the stream creation, stream synchronization, casting of stream IDs is also done automatically by our framework. Lastly, how good our framework has performed. We have performed our evaluation on 3 distinct platforms. The efficacy is that we have found 33 optimization opportunities in 26 different benchmark programs, and these optimization opportunities are all the optimizations, all the opportunities that were present in those programs. The analysis time ranges from few milliseconds to 1461. And the transformation time is ranging to 132 milliseconds. Effectiveness, we have performed our evaluation on the Polybench. We have gotten up to 3.2x speed up and with a geomean of 1.7x. For the Heckbench programs also, we have got up to 4.3x with a geomean of 2.2x. Finally, for the cases of profiling, we have shown this profiling also in our paper, that if you see that the memcopy device to host is not even overlapping in the baseline program. However, in the transform program below, it is overlapping. Same for the kernel-kernel overlaps, where 2 kernels computations are overlapping with each other. And these are also given in the paper. We have also performed a comparative study with the CUDA graphs and have got near to them and more than them performance on several benchmark programs. In summary, this is the summary. You can see for more details, you can see the paper. For more clarifications, you can send me an email via the web page. And there is a web artifact. Please download it and play with it. Yeah, thank you.
Awesome. Thank you very much. Do we have any questions? We got one in the back. Okay. I'll try not to use my own prerogative, but I do have a burning question myself.
Yeah, I really appreciate this line of work because stream-based programming is important, and it'll be good to pool benchmarks from what you have and some of the benchmarks that I have. In fact, there are other interesting cases where callbacks are also put into streams, and that introduces happens before that is slightly tricky to detect. So if you have you thought of things like that?
Yes, we have thought of that, and instead also we have put this in our in the future work of our paper, and we have put a discussions where we have a line of works that stream callbacks, multi-GPU setups. So all these we are trying to target in the future. So we have thought of that, yes.
That'd be okay. And unified memory combined with all this makes life more fun. Okay.
Yeah,
talk more,
exactly. About the unified memory, I have a clarification. We might be having a paper very soon on the unified memory-based optimizations. It is under submission, so I think you can see it soon. Yeah.
Do we have other questions? If not, I'll ask one. Oh, okay, I have to give David the opportunity. It's fine. Okay.
Were the CUDA stream synchronized calls just a simplification for the discussion, the talk? Or do you actually like synchronize the CPU?
Yeah, we see there are this, like CUDA provides us this stream synchronization calls, CUDA stream synchronize, which synchronizes the CPU thread until all the CUDA operations launched on that particular stream is finished.
So what is the reason for using that instead of a GPU to GPU synchronization?
GPU synchronization. So we have some other options, which is the CUDA event synchronization. So like one thing that when I built this whole project, I have kept in the mind of CUDA event synchronization. So, but when we saw that, okay, many people are not familiarized, or even some good GitHub APIs, they are pushing for the CUDA stream synchronizations instead of CUDA event. We are like, okay, let's fall back to the CUDA stream synchronizations instead. But this works fine with the event synchronizations as well. So if that answers your questions.
Yeah, it does.
Yeah.
Thank you.
Yeah.
Okay, why don't we go ahead and start switching over the laptops. May I ask a question while we're doing that? Okay.
Sure.
So this is maybe open-ended, but how would what would you consider to be the ideal way to assign streams to the different CUDA operations?
Okay, so we were trying to see for different GitHub projects, and then we saw these kind of issues that people were screaming around about.
Sure, yeah.
So we are like, okay, we need an automatic tool for that, but while solving the project, we are like, okay, this is not so easy at all, so we have to.
But do you have a sense of like, what even would be the criterion here, or what are some of the criteria which would make one stream assignment better than another, as opposed to a problem?
Oh, okay. So if you
assuming you have a choice of different valid stream assignments, right?
Yes.
Which one should we prefer? Under what criteria should we prefer one versus another?
Okay, so the criteria should be that where in all the operations will be overlapping as you want, or there is a maximum overlap between all the CUDA operations. That should be the ideal stream assignment.
Okay, got it.
Thank you.
Thank you for asking a question here. Everybody's thinning out, but it's, I know how to write GPU kernels. My whole GPU programming is all handled now. No, you got to deal with streams. In fact, it won't be in this talk, but another thing is all of the network communication, which has to be coordinated with that. So I think the stuff outside of the kernels is quite interesting. Anyway, we have another talk here from Zhe Yuan, and he will be telling us about, I'm sorry, I don't have the title up. Give me 1 second, I will do a better job. Sorry. Will tell us about, it's right there, SIMT step execution. Okay, flexible operational semantics. So a little bit more back to our high-minded PL. So take it away.
Oh, yeah. Oh, nice.
It's good. Okay.
Hey, everyone. I'm Jerry Chen from UC Santa Cruz. And today I'm happy to present our joint works, SIMT step execution of flexible operational semantics for GPU subgroup behavior. This work was done with Naomi from UC Santa Barbara, Guido from Microsoft Research, and Tyler from UC Santa Cruz and Microsoft Research. So here is the executive summary. So for this talk, I will use the portable GPU terminology here. So what could I call swap out? I will call work groups. And what could I call WAP? I will use subgroup here. So the problem we're trying to focus on is the subgroups are performance critical, but their semantics are often under-specified. And the SIMT step try to address this by providing operational semantics for subgroup behavior. And it models two things. First, which thread participates into a subgroup operation. And second, whether instruction execute independently, synchronously, or collectively. And we validate this with executable TI semantics and experiment on 10 GPUs from 8 vendors. So before jumping, I would like to give a little bit of background on the GPU architecture. So let's just start with the CPU side for comparison. So a CPU usually has a small number of relatively powerful cores, and each core can run a few hardware threads, and each core has a own private cache, and then the core can communicate through the shared cache and eventually through the main memory. So the hierarchy is fairly shallow. We can think of as CPU, then core, and then thread. But on the GPU side, the structure is a bit deeper. So at the hardware level, we have GPU that are made up by many string multiprocessor, or we call it SM, and together with the global memories. And now let's zoom into one SM. So SM is not just a single core, but it's a small parallel processor that contains many execution units, a large register file, and fast on-chip memory. And from the programming model point of view, where a kernel is launched with many workgroups, and a workgroup is a group of threads that can cooperate with each other. And the SM then schedules this thread into a smaller groups, which is subgroups. So GPU exposes many levels of parallelism and map a huge number of threads onto many execution resources, which make it scale. So we mentioned subgroup before, and let me officially introduce it. So a subgroup is a small group of threads that execute in a SIMT style, which is a single instruction, multiple threads, while the exact number of the subgroup depends on the platform. So on NVIDIA, it's fixed to be 32, but on other devices like ARM's Mali GPU, and maybe have the subgroup size of 16. And one of the craziest devices we've seen is a Qualcomm device. It has varying subgroup size. It means the subgroup size can range from 16 to 128, depends on how many threads you launch. But the point is that the subgroup is treated as an execution unit, and many operations are designed around this group. So modern GPU API also expose subgroup operations. These are operations that execute across the subgroup threads. So for example, subgroup add returns the summation of all participating threads values across the subgroups. And these subgroups are performance critical because they allow the thread to cooperate efficiently without going through to the shared memory or require full workgroup synchronization. While subgroup thread can also execute on the non-uniform control flows. That means in a same subgroup, some threads may take a branch, while others may take another branch. And if a subgroup operation appears inside one branch, then only the thread that reached to that branch will participate into that operation. Well, so here is an example showing how SIMT style execution model works and why subgroup operation is powerful with a concrete example. So for the talk, I will just focus only on one subgroups. So here is an example on how dot products works in GPU program. So each thread firstly has its own thread ID computed by thread ID.x. And here the highlight line compute the A ID times B ID. Every thread executes the same instruction, but because each thread has a different ID, they are operating on different array elements. Then each thread contributes the value to a global result using atomic add. So this program is not very efficient because if we launch n threads, we will perform n global atomic operations to get the results. Now we can optimize the SEM computations using a subgroup operation. So each thread still compute its own local value, but before going through to the global memories, the thread in the subgroups cooperate using a subgroup add, and this produces a one-value subgroup sum for the whole subgroups. And then only one slice thread in the subgroup will perform the global atomic add. So instead of the one global atomic per thread, we now have one global atomic per subgroups. So this exactly shows why subgroup operations are powerful. But now the program is no longer just ordinary thread level code. Its correctness depends on the subgroup level behavior. And we need to know which thread participates into this subgroup operation and which synchronization that the subgroup operation imply. So here are the two questions that motivate this work. So the first question is which thread participates into a subgroup operations? To address this, we introduced dynamic block, which gave us a precise way to track the runtime subgroup executions. And the second question is, what synchronization or synchronized subgroup stress? And our second contribution, SIMT step models, answer this by giving a spectrum of the possible subgroup semantics. And a different model classify instruction as independent, synchronized, or collective. And our third contribution as an empirical study, we design and run distinguished tests for different semantic model we propose on real GPU and to see which behavior actually happen in practice. So for this talk, I will only focusing on the second question because of the time. So to motivate the second question, we can first looking at the lockstep intuition behind the subgroups and why modern programming languages are more cautious about relying on it. So in CUDA, the corresponding concept of subgroup is warps. And the early CUDA exposed warp-level operations like any and all, which takes the Boolean expressions and return true if any or all participants evaluate the expression as true. So this operation encourages programmers to think of warp strat as execution units. And then later, CUDA added shuffle intrinsic, which led strat to exchange the value directly within subgroups. This made subgroup level programming even more important for the performance. But over time, relying on the implicit lockstep becomes less stable as a programming language assumption. And this is the historical point I want to highlight. So in CUDA 4.2 programming guide, there was an example like the code shown on the right-hand side. This example relies on the assumption that subgroup execute a lockstep to make the computation to be correct. However, at CUDA 5.0, they totally removed the example from the programming guides. And this documentation change suggests that implicit locksteps should not be treated as a formal programming model guarantee. So this shift becomes especially visible with the new architecture like Volta and the CUDA 9.0, where NVIDIA introduced the independent strat scheduling, where each strat now has its own program counters, and add the explicit warp-level synchronization. As for today, there is only a fragment guidance on subgroup behaviors, and subgroup lockstep may be a useful intuition, but it's not something we should assume without precise specifications. So that's the reason, at least to the second question of the paper, to what extent is the subgroup execution synchronized across the stack? So in our paper, we have proposed several synchronization models, and collective memories, or SM, is the strongest model we propose. And the question this model is trying to answer is, when multiple subgroup strats reach the same memory operations, do they execute as an unrelated per strat step or one collective subgroup step? So in this example, both strats are in the same subgroup, and they both write to the same location with their strat ID. So this is conflicting writes. On the collective memory, the store instruction is executed as a subgroup level collective memory. So then both strats execute the load. Under collective memory, the load operation is also collective. So the both strats must observe the same values from the location. It could be 0, it could be 1, but both strats should observe the same values. Therefore, the assertion at the first line should pass. It's a very convenient model for a programmer because it gives a strong lockstep style intuitions. So to test whether the real GPU support collective memory, we start from the previous example as a base test pattern, and then use fuzzing to generate 10K variants and run them across different GPUs. So in the heat map, green means that we did not observe any relaxed outcomes, while red means at least one relaxed outcome was observed. Here I'm showing the device where the collective memory behavior still appears to hold, which is the NVIDIA and Apple device. But for Intel, ARM, and the Qualcomm device, we see many relaxed outcomes. Samsung is interesting. It only shows one relaxed outcome, but since they're so rare, we should be careful about that. It might reflect the intense hardware semantics, or maybe also compiler or driver bugs or interaction with the memory model. But the point is that the collective memory is attractive, but it's not a portable model for real GPUs. Now we have another model on another extreme, which is independent execution, which is really relaxed. This example shows why fully relaxed subgroups execution can lead us to a semantic swarm. So under fully independent execution, a thread may run ahead. So in here, we assume T0 runs first. So it loads the X, which is 0, into its local variables. And then T0 evaluates the condition as true. So it enters the branch. And it reaches the subgroup at which if we allow very relaxed subgroup behavior, T0 might speculatively execute this subgroup operation, assuming that T1 will now join these operations. And then T0 will change the value of x, which store 1 to x. Later, T1 runs and it loads and it says x equal to 1. And T1 will just skip the branch. So the speculation is now effectively justified by the later execution. T1 does not join because T0 already changed the value that control whether T1 will enter the branch. And this is what I mean by semantic swamps. If a subgroup execution is too relaxed, the participant set is no longer determined in a clean and structured way. Instead, it can depend on the speculative assumption and later action that makes this assumption to be true. And this is a controversial example that raises a lot of discussion in the internal kernels group. So collective memory is too strong, and the independent execution is too relaxed. So we want to find a middle ground. So that's why we propose synchronized control flow, or SCF. So in SCF, the memory operation may execute independently, but control flow provides synchronizations. So the thread will synchronize and collectively execute the branching instruction. So in this example, since the F statement works as the synchronization points, both threads will load X before the branch is resolved. So both threads say X equal to 0. And both threads will synchronize at the F instruction. Then they will enter in the F block. Then the subgroup operation inside the block has a well-defined participant set, which is T0 and T1. So the key idea is that the SCF will keep just enough structure to avoid the semantic swamp that what we show in the fully independent execution. So now we can organize this model into a spectrum. So moving from left to right, the model provides less synchronization and give implementation more flexibilities. CM is the strongest ends, and CF sets further into the right, and the other model fit into the design space between these points. So as you can see, the symmetry step is not a fixed semantics. It's a framework for describing multiple specifications by deciding where subgroup synchronized comes from. So the formal model tells us what different specification could allow. But we also want to know what real GPU actually do. So we design a small test that distinguish between the different symmetry step models. So each test is constructed so that a relaxed outcome is possible under a weaker model, but forbidden under a stronger model. Then we generate this test into a 10-base patterns, generalize this test into a 10-base pattern, and generate 10K false variance per base test. And we run them on 10 GPUs from 8 vendors. Well, here's the overall results. So the first takeaway is that the most device behaves strongly synchronized in our test. And the second takeaway is that the collective memory is too strong for many platforms. Many GPUs do not behave as if the memory operation were collective across the subgroup threads. And the third takeaway is that real no synchronized observation remain inconclusive. We try to investigate them, but could not determine whether they comes from the intent hardware semantics or relaxed memory behavior, or they are just purely driver or compiler bug. So to summarize, dynamic blocks solve the participant problem. They tell us which thread execute the subgroup operations, especially under divergence. And the symmetry step model gives us a spectrum of the subgroup semantics models. And the TI plus implementation and the GPU experiment give us a reality check to show which behavior are possible in the models and which behavior appears in practice. Yeah, I think that's all of my talk. And I'm happy to take questions.
Okay, do we have any questions here? Any takers? Thanks, Shweta.
I mean, in the worst case, assuming that all of the observed misbehaviors you see are due to hardware semantics, where does that leave us in terms of what is the semantics that we should be expecting? Like if you go to your results graph, is there another model that maybe?
Well, I would now, trying to advocate just one semantics model, because as you could see, different devices shows different synchronization levels. That's why we give a spectrum of the semantics model. But just from our empirical results, it looks like most devices support the SCF, which is synchronized control flow. But we do see some, rare, relaxed outcome that we could not determine whether, their compile bugs or other issues. So the work is mainly, the contribution of the work is mainly as a foundation for the compiler writer and the language designer to know like which outcome might be allowed under different, semantics. Yeah.
Do we have any second questions? I can ask one if not. So this is a really naive question. Just like,
yeah.
I think I always feel like, oh gosh, I still don't understand memory models. And this feels very much in that space. But I wonder sometimes, like we are often interested in getting a very precise characterization of how the hardware behaves and what the guarantees it's providing. And this is certainly important for forwards compatibility because someone might exploit that and it's worth specifying. Do you have a sense of how much this divergence of behavior is a problem for real CUDA programs or real GPU programs?
Well, I mean, at least for the collective memory, we are certainly sure that there are, they show, violations. So that's certain. But for other real behaviors, there might be issue with the weak memory model. But we also try to test whether, the device we have shows some weak memory behavior. So one of our students in our labs have a works about, testing the weak memory behaviors. And we try to, using the same, using the same strategy to test if this device really shows weak memory behavior, but no of them shows. But we still are now very conclusive about this because we try to, the test of the fuzzing, they have like thousands of lines of code, and after you manually reduce them, they still end up having really long of code, so that's why we are inconclusive. So yeah.
Cool. Thank you very much. Let's give Zheyuan another round of applause. And to close us out, we talked about programming the kernels, we talked about sticking them in streams, we talked about verifying things. But did you know that GPUs can be used from the web as well? Oh my gosh, it's true. And so, well, do we have a slight AV? Oh, cool. Can you hear me by any chance? It's true. In fact, not only can you use GPUs to do machine learning, you can use them to do graphics. It's really shocking. So these shading languages are very nice for that.
Well, although you can use it to do graphics, we'll actually mainly be talking about compute programs. So,
dang it.
A bit of a bait and switch there. But yes, I'll be talking to you about the uniformity analysis in the web GPU shading language. And this was joint work with John Wixon and Alistair Donaldson at Imperial College. So synchronizing GPU programs is a tricky business. So consider the following CUDA program, which is being executed by 2 threads. I'm also going to use the platform agnostic term workgroup. And in this program, when these 2 threads execute, each of them will have a unique ID. And in CUDA, that unique ID is held in the special variable thread ID x.x. And what these unique IDs do is they let different threads take distinct paths through the program. So when thread 0 executes this program, it's going to try and assign the value 0 to both elements of this array A. And when thread 1 executes the program, it's going to try and assign the value 1 to both elements of the array. And I'm sure many of you will notice that there's a big problem with this program, which is that it has a data race. So the updates performed by thread 0 and thread 1 are going to race with one another. And this is a problem because data races are a form of undefined behavior in many GPU programming languages. So this program may reasonably do anything. To resolve this particular problem, GPU programming languages provide a construct called the barrier. And the way a barrier works intuitively is that when a thread reaches a barrier, it will wait until all other threads in a work group reach the barrier, and then they will traverse it together with a consistent view of shared memory. And so in CUDA, a barrier is provided by this sync threads function. And what that's going to mean for this program is that these first 2 array updates A are going to be performed first, they will reach the barrier, they will wait for the other thread, and then they will move on to performing these array updates afterwards. And we can see that this resolves the data race that we had previously. So barriers are often necessary to avoid data races in GPU programs. But the problem is that misusing barriers can result in another form of GPU undefined behavior. And that undefined behavior is called barrier divergence. So in this CUDA program again, we can see that this time, thread 0 is going to reach this first barrier, and thread 1 is going to reach this second barrier. And so I mentioned before the intuitive way that barriers work is that when a thread reaches a barrier, it will wait until all of the threads in the workgroup reach the barrier, and they will traverse over the barrier together. But in this program, there isn't a barrier that is reached by all threads, and so it's not really clear how to give semantics to a barrier in this context. And so for that reason, GPU programming languages eschew barrier divergence as a form of undefined behavior as well. And so this program may crash, it may hang, or it may do anything else. And in practice, it will probably hang. So while this is acceptable for languages like CUDA, where you write your own kernels and it's intended for experts, it is not acceptable for a web-based programming language. WebGPU is a new programming model for the web, and it brings general-purpose GPU computation to the web for the first time. It's centered around a JavaScript API for interacting with GPUs via the browser, and programs are written in a new programming language called the WebGPU shading language. And so this language is designed in a way such that it does not have the undefined behaviors that you would find in other GPU programming languages. So just to give you a bit of intuition about the way Wigzil works, and Wigzil being WebGPU shading language, you might load a web page and it might have a Wigzil program embedded in it. And the goal is to compile that to something that can run on your GPU. And although I've picked something that looks like a discrete GPU here, because it's a web-based programming language, it needs to work on mobile devices, integrated GPUs, everything. And so rather than trying to compile Wigzil directly to GPU machine code, instead, Wigzil is compiled to existing GPU shading languages. And the shading language chosen depends on your system. So on Linux, Wigzil is compiled to SPIR-V, on Windows it's compiled to HLSL, and on Apple it's compiled to MSL. And your browser is responsible for doing this compilation. So Chrome has a Wigzil compiler, Firefox has a Wigzil compiler, and so does Safari. And then this means that the language tooling for HLSL, SPIR-V, and MSL can deal with compiling to something that can run on your GPU. Okay, so the problem is that SPIR-V, HLSL, and MSL all treat barrier divergence as a form of undefined behavior, much in the way that CUDA does. And so if we were to write a Wigzil program that had barrier divergence, so this is exactly the example we saw earlier, where workgroup barrier is now our synchronization barrier, and LID holds the unique variable of each thread. If we compiled this faithfully, we might expect that our browser would hang, our display would freeze, and that would not be good. But thankfully, if we try and compile this program using the Chromium implementation of a Wigzil compiler, we'll get an error that looks like the following. And here the compiler has done a good job. It's rejected this program, and you can see that we've got this error saying workgroup barrier must only be called from uniform control flow. And the reason that we get this error is that the Wigzil language specification defines a static uniformity analysis that implementations of the language are required to implement. And the goal of this analysis is to rule out all programs that would have barrier divergence and reject them at compile time. While this is a great idea, this analysis has several problems. The first is that although the analysis claims to be sound, there is no definition of what it means for a Wigzil program to have barrier divergence. And actually, it's kind of worse than that, because in the language specification, the analysis is claimed to be sound, but then later in the language specification, it says that a program is defined to have barrier divergence if it is rejected by the uniformity analysis. And so this has a certain circular shape to it. And then the second problem is that the specification of the analysis is just long and imprecise. And in particular, it takes up 27 pages in the language specification, which can make it a little bit hard to figure out what the analysis is trying to do. And in particular, it was often easier to refer to the Chromium implementation of the analysis to try and figure out what was intended. On top of this, implementations of the analysis are just fundamentally hard to test. It's difficult to come up with a way to construct an input program and whether the analysis should accept or reject that program. And then on top of that, when we did do this, we did test implementations of the analysis, we found several soundness and precision issues related to the way the analysis was formulated. So for the rest of the talk, I will talk a little bit about how we approach these problems. So this is the example that I referred to earlier, and barrier divergence relates intimately to this idea of uniform and non-uniform control flow. Non-uniform and uniform are a little bit overloaded here, so I'll tell you what I mean by these terms. By uniform control flow, I mean some piece of control flow that is executed by all threads in a work group. So at the beginning of this main function, both threads would start executing here, so control flow is uniform. In the case of expressions, an expression is considered non-uniform if it would dynamically have different values in different threads. So this Boolean condition is going to evaluate to true in thread 0 and false in thread 1, so it's non-uniform. And because this expression is non-uniform, control flow inside the if statement is also non-uniform. There is no branch in this if statement that will be executed by all threads. And so there are roughly two conditions for dynamically defining barrier divergence. The first is that there is an execution where at least two threads reach different barriers, and we've already seen a case of this. And the second is that two threads reach the same barrier but under non-uniform control flow. And I don't have much time here to give you a precise definition of non-uniform control flow. So hand-waving a little bit, and the precise definition being in the paper. This program on the right is an example where thread 0 and thread 1 will reach the same barrier, but they will take different calls to F, and they will reach that same barrier. And for a bit of intuition, the reason that it's desirable to consider this undefined behavior is that the compiler will probably want to inline that function F, and if it does so, we'll end up with exactly the program we saw before, which has undefined behavior. And like I said before, this is defined completely precisely via an operational semantics in the paper. But without going into any detail, the main rule is this barrier error rule. And in particular, this condition is quite important. And this condition says that barrier divergence occurs if there are two threads that reach different barriers, or there are two threads that reach the same barrier having taken different control flow, with the latter condition being represented by kappa I is not equal to kappa j. And in this case, we transition to a special error case representing the fact that barrier divergence has occurred. Okay, so now we have a rigorous definition of barrier divergence, but we still haven't solved the fact the analysis is lengthy and imprecise. So uniformity analysis is this static taint analysis that is syntax directed and that claims to be sound. And importantly, although it claims to be sound, it's not complete because the analysis is value insensitive. So although the expression LID is equal to LID will dynamically always evaluate to true, the analysis conservatively considers it to be possibly non-uniform. So this is the example we've seen before, a nice contrived example, but it will help to demonstrate the analysis. And the analysis builds a graph, and it is centered around these two special nodes. The first special node is maybe non-uniform, and what this node does is it taints expressions and control flow as being non-uniform. This is a static taint analysis after all. The second important node is required to be uniform, and this is going to indicate that some piece of control flow or some expression must have a uniform value or must uniformly be executed by all threads. There's also this third special node, CF start, and this represents whether control flow is uniform at the beginning of a function. So to analyze this program, we first need to determine whether the expression LID is equal to 0 is uniform. And whether it is going to depend on whether LID is uniform, and we know that it's not, because LID is going to have a different value in all threads. And also, whether control flow is uniform in the branches of this if statement are going to depend on whether control flow is uniform before the if statement. And so we add this second edge from LID is equal to 0 to CF start. Then we go on to analyze the barriers in the body of this if statement. And because a barrier must be called in uniform control flow, to indicate that, we add an edge from required to be uniform to LID is equal to 0, to say that whether control flow is uniform at this point depends on whether LID is equal to 0 evaluates to the same value in all threads. And so now you can see that we have this path from required to be uniform to maybe non-uniform. And this is bad. This will cause this shader to be rejected by the analysis because some piece of control flow that must be executed by all threads may not be. And so for a slightly more complicated example, which I don't expect you to look at in too much detail, this analysis does work perfectly well with loops. So the program on the left has barrier divergence. And a couple of things to point out. You can see now that this graph on the right has a cycle to represent the fact that we have a loop. And we still have a path from required to be uniform to maybe non-uniform, but it now makes use of this loop back edge to represent the fact that whether control flow is uniform at a loop head depends on whether control flow is uniform at the end of a loop body. And again, we give a completely precise definition of this analysis in the paper, but we won't go through that here in too much detail. Okay, so we also give a proof sketch of soundness based on these two things in the paper, but we won't go through that here. The next problem that we tackled was testing implementations of the analysis. And to do this, we made use of a tool called Alloy. And Alloy is a modeling language that lets you write logical constraints that implicitly describe some system. So, for example, you might write some constraints that implicitly describe the shape of valid Wigzel ASTs. You might then also write some logical constraints that describe how a graph that is built by the analysis is related to a program AST. And this by itself is not very useful, but Alloy comes equipped with a tool called the Alloy Analyzer. And what that lets you do is generate witnesses for these sets of constraints. So what you could do is you could ask Alloy to give you back a witness, and it might give you back the AST that we saw before. It might give you back the program if LID is equal to 0, then barrier, else barrier, and it might give you back the uniformity graph shown on the right. And so while this is not very interesting in its own right, what we can do is add more constraints that give us more interesting programs. So we might ask for a program with 2 loops, for example, and Alloy might give us back this nested loop example, where we have a loop, and a break in the inner loop. And it would give us back the graph that corresponds to this example. Where this gets really powerful is that we can ask for constraints on the actual analysis graph. So we could ask for Alloy to give us an analysis graph that has a path from required to be uniform to maybe non-uniform. And if you recall, that means a shader that will be rejected by the analysis. And so Alloy might give us back exactly the program we saw before. What we could then do is give this program to an implementation of the analysis and check that it does what we think is the right thing. So in this case, it should reject the program because it has barrier divergence. Right, so now we have a way to test implementations of the analysis as well. During this process of both formalizing the analysis in Alloy and testing implementations with the Alloy formalization, we found a soundness bug. And I'll give a brief explanation of this soundness bug. So looking at this program on the left, you can see that we have a loop. And you can think of that like a while true. It's specific to Wigzell, but it's effectively while true. And at the end of this loop, we have a break if expression, which is going to cause the loop to break if LID is equal to 0 is true. And so what's going to happen is, on the first loop iteration, every thread is going to hit the barrier, and then thread 0 is going to break this loop, and all the other threads are going to come back up and execute this barrier. So because not all threads are going to reach the header of the loop on the second iteration, control flow is non-uniform, and so this is a case of barrier divergence. In this case, we would expect the analysis to give us a path from required to be uniform to maybe non-uniform, but this graph shown on the right is the graph that the analysis would have given us. And you can see that there's no path from required to be uniform to maybe non-uniform, indicating that the shader would be rejected. So really, there's a missing edge in this graph, which is the one shown in red here, which says that whether all threads reach the end of the loop body depends on whether the expression LID is equal to 0 evaluates to the same value in all threads. So now we do have the path that we'd expect. So we reported this, and it was accepted into the language specification. Alongside this soundness bug, we also found several precision issues that allow through more shaders, and this is particularly important because shaders that fail the analysis will just not be compiled, so they won't run at all. And again, we also found several just editorial improvements that make the spec more precise and easier to read. And interestingly, we also found a very basic parser bug in Chrome, which was also fixed. Okay, so now we've fixed all those problems, and just to recap. In part of this work, we gave a precise operational definition of barrier divergence for a subset of Wigzell. We gave a precise definition of uniformity analysis. We had several fixes that were accepted into the language specification related to precision and soundness. And we give a concrete Alloy model for testing implementations of the analysis. So I guess the main takeaway from the talk is that applying lightweight formal methods to industrial programming languages can reap quite a lot of benefits. And so if you're interested in that, feel free to come talk to me after, and I'll take any questions that you have now.
Do we have any questions in the audience? Two here.
Thanks. Thanks, James. So one thing I was wondering is, so you looked at Wigzell here, but as we've seen throughout the session today, there's a billion GPU languages, and I would like all of them to detect if my barriers are right or wrong. Like, in your analysis, how specific is this analysis to Wigzell, and do you think it could extend to other GPU languages? Like, what assumptions are you making about this?
I think it could certainly be extended to other GPU languages. It's in no way particularly specific to Wigzell. Wigzell has a smaller set of constructs, I guess, than other GPU languages. So the main synchronization primitive for compute shaders is the workgroup barrier. And so I guess you would have to work out how to extend it to other GPU synchronization primitives, but I see no reason you couldn't do so. So another thing that you could do if you did extend it to other GPU programming languages I mentioned here that the analysis isn't complete. It's not value sensitive. And that's intentional here. The analysis is meant to work somewhat like a type system, so it's predictable. If the analysis depended on the values in the program, you might update your value analysis, make it more precise, and it might be hard to predict whether your shader is going to be accepted or not. And that would just also be hard to formalize in the language specification. But if you wanted to write an extension of this analysis, say for CUDA or another language, you could make it value sensitive, and you could make the analysis far more precise. So that seems like it could be a valuable pursuit.
One more question here.
Actually, two more. No, myself too. Okay, I see. Then I'll just quick. This could be a very dumb question. I don't know much about this barrier thing, but does it normally happen to people trying to put barrier inside the loop?
It depends. There are situations where you'd want to do it. So one of them is, say, you had an array and you wanted to sum all the elements of the array. One way that you can do that is a sort of tree-style reduction where you get threads to add up pairs of elements in the array. So first, say your array is double the length of the number of threads you have. You have each thread take 2 elements and sum them, take 2 elements and sum them. You then disable half the threads, you do the same again, and you keep going. In that case, what you need to do is you need to make sure that you synchronize all the threads on each array iteration or each loop iteration. Otherwise, you're going to have threads accessing overlapping array indexes on each loop iteration, which would be a data race again.
Okay, thank you. I think that about closes it for the GPU session. But don't worry, there's plenty more GPUs to be found here and at other conferences. So let's give all of our speakers another quick round of applause. And I believe we have the student posters this evening, and